Right. Good morning, everybody. It is my great pleasure to introduce Dejan Goetz from University of Ljubljana, who is going to tell us about surfaces in the D cube.
Yeah, it's a great pleasure to be introduced by Ran, and I would like to thank the organizers for giving me the opportunity to speak here. So today I will talk about some joint work with Andrea Aveni and Erika Roldan, who are based in Leipzig mostly, although also well connected with other places as well. As you can see from the title, I'm going to talk about surfaces in the cubes. So first, it probably makes sense to focus a bit on the more well-known case, which is surfaces in the simplex. So these are called also triangulated surfaces. So triangulation is one of the basic methods to represent spaces in a discrete form, which makes them amenable to computation and all sorts of things. So then it is also desirable to know what are the minimal triangulations, for example, and this is what we can see here in this picture. So the first one is the triangulation of RP2, represented conceptually as the quotient of the icosahedron with respect to the Z2 action, which is why it's also known as the hemi-icosahedron. And then the other one is the famous Möbius minimal triangulation of the torus with 7 vertices. These two you may have seen, especially the first one is quite famous, but in fact, the triangulations of all surfaces are well known. I'm going to need the following notation in my talk. I will use it pretty much on, well, most of the slides, I'm guessing. So this is a good time to pay attention. So sigma G is going to be orientable closed surface of genus G. And NK is going to be a non-orientable surface of demigenus K. In other words, a connected sum of K projective planes. So by the classification of surfaces, these are the only possibilities. And as it turns out, by this nice theorem of Jungermann and Ringel, we can say exactly what the minimal triangulations of these closed surfaces are. So a closed surface has a triangulation with n vertices if and only if n satisfies this bound, which historically first appeared, I think, in connection with the four-color theorem. So it's also known as Haywood's bound in the literature. And this turns out to be also sufficient for triangulations of surfaces, except in some cases that are listed below there, which are sort of more difficult to triangulate. Okay, I will also briefly describe the idea behind this proof. So first of all, where does this bound come from? So this is the necessity part of the argument. So if you write down the Euler characteristic of a triangulated surface, it has that expression you can see there in the first line. But since it's a triangulated closed surface, you know that every edge has to be contained in exactly two faces, and the faces are triangles. So you get the equation that 3 times the number of edges is equal to 2 times the number of faces. So usually people in this area use this F vector notation. So Fi means the number of I-dimensional faces. And anyhow, from these two equations, then you can express the number of edges explicitly in terms of number of vertices and the Euler characteristic. And then since the number of edges cannot be greater than the number of edges in a complete graph, you get this bound that this number is less than or equal to n choose 2. And then after solving for n, you get exactly this Haywood's bound. And the nice thing is that it turns out that this is also sufficient. So this is the non-trivial part of the proof of Jungermann and Ringel, and they spend the rest of their 30-page paper discussing the sufficiency part, so constructing all possible triangulations of this kind. Okay, so one thing that we learn while doing this is that the f vector of a triangulated surface is completely determined by the number of vertices and the Euler characteristic. It has this explicit formula that you can see there. So from this bound, we know everything about possible f vectors of such triangulations. Okay, now moving on from surfaces to triangulations more generally, things become much more non-trivial. Minimality for general manifolds and more general spaces is wide open. I'm going to present a few conjectures and questions that people have been considering. So there's this beautiful conjecture by Kühnel and Lastmann, who have both worked a lot in this theory of triangulations. Especially Kühnel, I think, was one of the names associated with almost every result in this area from the 70s and 80s, probably more 80s. But so they constructed a family of triangulations of the n torus with this number of vertices that you can see there. And while new families of triangulations have been produced in some cases, none of those have changed this bound in any way. So Kühnel and Lastmann conjecture that this is in fact the minimal triangulation of the torus. But this conjecture, last I asked, was not even known for the 3 torus, so the simplest case after the 2 torus. So like I say, everything here is wide open. Then you can ask the same question for RPN. So people have worked a bit on this. So the first family of such triangulations was again produced by Kühnel, I believe, perhaps someone else as well. And they required the same number of vertices as the triangulations of the tori. So it was exponential, and the base of the exponential was 2. Then recently, I think maybe 5 to 7 years ago, I don't remember exactly, more like 7 probably, some students of Isabella Novick, I think it was Venturello and Zheng, showed that you can also find different kinds of triangulations of RPN, which sort of do a 2-step recursion, and then you get some sort of Fibonacci numbers for the vertices. Okay, but then the lower bound, the best lower bound that's known in this case is quadratic in n, which is quite a big gap. And it has been only recently that people produced triangulations that actually require less than exponentially many vertices. So this is a recent result by Adiprasito, Avakumov, and Karasev. And so they produced triangulations that require e to the square root of n log n or something like that vertices. Yeah, so, but the lower bound is still quadratic. So in principle, they could also be polynomial, but no one knows how to say anything about that really. Okay, another space that's quite pretty. So there's this paper by Björner and Lutz. Yeah, Lutz, who sadly passed away recently. Lutz has this nice survey paper about minimal triangulations, and he pretty much lists everything that's known about them in that paper, or that was known up to that point. And so he also has a paper with Lutz where they show that there's a 16 with Björner, so where they show that the 16 vertex triangulation, there's a 16 vertex triangulation of the Poincaré sphere. also known as the Poincare dodecahedral space because it's a quotient of a dodecahedron. And they have some nice pictures of these triangulations there as well. So this was produced by Lutz software called Bistellar, which uses bistellar flips to so this is some sort of combinatorial operation that you can use to modify triangulations, and he used it to find a lot of these minimal triangulations that are now known after that previous work. So this vertex is this 16 vertex triangulation is conjectured to be minimal. But also no one knows how to prove it. So recently, we made some progress on this question by enumerating all possible fundamental groups of complexes on 8 vertices. So you can show that if there is a let's say 13 vertex triangulation, 12 vertex triangulation of the Poincare sphere, then what you can do is you can sort of remove the top simplex. You are left with 8 vertices, but that complex that you obtain will still have the same fundamental group because you just punctured the manifold. Yeah, so if the fundamental group of the Poincare sphere, which is the binary icosahedral group, doesn't occur on 8 vertices, then you know that there's no such triangulation. So by enumerating all of these fundamental groups of simplicial complexes, we established that you need at least 13. So the best known result before, I believe, was 12. Due to Bakci and Data, who did this huge combinatorial argument where they showed that this was not possible with 12 vertices. Okay, but yeah, there's also a gap here. Okay. Finally, you can also ask how many vertices are needed to triangulate some homotopy type. So if you're only interested in triangulations of spaces up to homotopy, there's this nice invariant introduced by Karoubi and Weibel called covering type. So they were investigating some questions about generalized cohomology theories, and so there you have some sort of Meyer-Vittoris arguments, and then they wanted to know how many elements you need to produce a good cover of a space homotopy equivalent to what you're interested in. And so they call this invariant covering type, and it's also equal to the minimal number of vertices needed to triangulate a space up to homotopy by the Nerv theorem. Okay. So this theory of covering type is also quite interesting. So from the definition, you can see that it's closely sort of related to the Lusternik-Schnirelmann category, except that it looks at good covers rather than categorical covers. Yeah, so what you can do then is you can produce some bounds based on the category and bounds based on cohomology. And most of these bounds turn out to agree with known bounds that we had for triangulations from before. And there's actually a result by Borghini and Mignan that the covering type in the case of surfaces is actually equal to the minimal number of vertices in the triangulation, except for the curious case of surface of genus 2. For the orientable surface of genus 2, you can actually do it up to homotopy with 9 vertices, but to produce an actual triangulation, it requires 10 vertices. So you can spare 1 vertex by doing it up to homotopy. Okay, as you can see, lots of stuff to work on. I mean, mostly we would need some new theoretical tools to attack these problems, probably. So yeah, I mean, if anyone has ideas, that's what's needed to make progress here. But anyhow, this is not what I'm going to talk about today, really. Yeah, so simplices are not the only thing you can consider. So if a triangulation of a space is means representing a space as a subcomplex of a single simplex, then you can also ask, okay, but then what is the minimal cube that I need to represent a surface in? So that's one sort of question that you can ask. The other question you can ask is also vertex minimality again. Oh yeah, okay. Right, probably should have permuted the slides a bit, but yeah, because now I'm already talking about minimality. Yeah, the situation for cubes is a bit different from that of simplices, because for simplices the minimal number of vertices is also well, sort of differs by one from the minimal embedding dimension. So if you can embed it in an n simplex, then that means you can triangulate it with n plus 1 vertices as a subcomplex. For cubes, this is not so. So if you can embed something in the D cube, that doesn't tell you how many surfaces you used to do so. So you have two notions of minimality for cubes, making the thing a bit more complicated potentially. Although I think we don't know of a single example where you cannot produce the homotopy type inside the cube if the bound on vertices is satisfied. They probably exist. That would be my hunch. So, okay, anyhow. So simplicial complexes are nice because you can represent any finite CW complex up to homotopy as a simplicial complex. The same is true for cubical complex. In fact, if you can triangulate something, there's this nice construction that allows you to sort of translate that triangulation into a subcomplex of a cube that has the same homeomorphism type. And the basic observation there is that sort of the link of a vertex in a cube is combinatorially looks the same as a simplex. So that's sort of what you do, and this gives you a construction. In particular, when we applied this to the minimal triangulation of RP2, we obtained this beautiful picture here. So this is the minimal realization of RP2 in the 5 cube. You cannot do it in the 4 cube. And I believe this is the first time this minimal cubical realization appeared. So in particular, an RP2 in the 5 cube was known before, but it was not minimal. I will tell you more about that a bit later. Okay, anyhow, so one thing that makes simplices great is that they have a very simple combinatorial structure. So you can basically represent the simplicial complexes as in the abstract form using subsets of the vertex set. For the cube, we also have a nice structure, but it comes from this product structure that you have on the cube. So if you have this, so any cube is the product of D copies of the unit interval, and then the cell structure on the cube comes from this structure on the interval, which has 3 cells, which we will encode by zeros, ones, and stars. Yeah, actually, I don't think I will really use this. I use this in my algorithm then when I enumerate stuff. But yeah, for example, under this encoding, the RP2 from the previous example can be represented by listing the top cells, which in this case are such sequences. So in particular, a D cube would have 3 to the D cells, whereas a simplex has what, 2 to the D plus 1, minus 1 if you don't count the empty set. But here in the cube, there's really no such thing as empty cells, so it's a bit different in that respect. Okay, yeah, for example, such a sequence, so this sequence that you can see there encodes the product cell in the obvious way. Okay, so we have a way of representing this combinatorially and hence also explaining it to the computer. Okay, minimality, I already mentioned this. Then the next question would be, okay, what is known about this minimality? And so what has been studied in the literature mostly is this first question of minimal embedding dimension. But so far, I think almost nothing is known about stuff like minimal number of vertices or F vectors. So there is some notion of cubical H vector due to Ron Adin, which but that deals more with abstract cubical complexes, and subcomplexes of cubes are much less general than that. For example, as an abstract cubical complex, you can glue 3 squares together edge by edge, sort of cyclically, and that cannot occur in a cube because there's no odd cycles in a cube. Okay. Anyhow, so yeah, minimal embedding dimension has been studied before. So similarly to how we figured out what the F vector of a triangulated surface is before, we also have bounds for the cubical surfaces. You use essentially the same computation. So you write down the Euler characteristic, then you write down the condition that faces are squares and each edge is contained in exactly 2 faces. And then you can calculate the F vector explicitly in terms of the number of vertices and the Euler characteristic. From this, you can immediately get a bound on the genus, which is this weird looking exponential thing here. And as it turns out, this bound can actually be realized always. This is a result due to Coxeter, who was studying a lot of polyhedral stuff, especially in the more symmetric cases. And he found this family of sort of maximal genus surfaces in the cubes. Yeah, and so these genera grow quite fast, actually. So you get what in the one cube. I will show you a table later, but for example, in the one cube, in the 3 cube, you can only get genus 0 because you only have the sphere, which is the boundary of that cube. While in the 4 cube, you can realize the torus. Then in the 5 cube, you can already get the surface of genus 5. In the 6 cube, it's surface of genus 17 and so on. And it, as you can see, it grows quite fast. Okay. The same idea also bounds non-orientable surfaces, although that's not the full story here. I will tell you more about that later. In particular, this maximal genus that you see here cannot always be realized. I believe that's a new result by us. And I will also explain why that is the case. Okay, but of course, then you can ask what happens with this intermediate genera. So if you don't only look at the maximum possible thing that embeds in the cube, can you embed everything in between? So sort of is embeddability monotonic in the genus. It turns out that for orientable surfaces, embeddability is very much monotonic in the genus. So you can realize any orientable surface that satisfies this bound that I showed you. This is a result due to Christoph Schulz. I will actually say a few words about the proof because the idea is not very complicated. And he also produced some bound for non-orientable surfaces. For non-orientable surfaces, he managed to show that you can always embed it in 1 cube higher than what the bound would suggest. But if you can embed it in the D cube is sort of more complicated. So he was able to show that you can do it for even demigenera. And he needed to assume that the dimension of cube is at least 6. So his result for even demigenous then works from 6 cube onwards. And you can actually realize any even demigenous surface that satisfies this bound, assuming that the dimension of the cube is at least 6. However, for odd demigenous, he didn't exactly get the exact result, so this case is partially open. Okay, so it would one thing that would be interesting to do then would be to try to complete this classification, which is something that we haven't quite succeeded doing, but I will explain why it might be a bit more complicated than it looks. Okay. So the idea of proof in this case is by induction. Basically what he does is he produces some constructions that he can use to build more and more surfaces out of some basic cases. So he starts by constructing the non-orientable surfaces in the 5 cube of demi genera 1, 2, 3, 6, and 8. He does this explicitly, although his constructions are not minimal in many cases. So for 1, 3, and 6, he gives something non-minimal. So that picture of RP2 that I showed you had 21 vertices. He gives a construction with 27 vertices, for example. But the even ones, I think he does well, except the 6. Okay, so 2 and 3 he does optimally. No, sorry, 2, 4, and 8. Yeah, sort of the powers of 2, I guess. But anyhow, okay. So then he also constructs the torus. So torus is quite easy to do. I don't have a picture here, but what you do is just you take the boundary of a square, and then you take the Cartesian product of this boundary of a square with another boundary of a square. And this obviously lies inside the 4 cube. So, and is in fact minimal, and we can also prove it. Now, then to complete sort of this collection of demigenera, he also needs to consider the surfaces of demigenus 32 and demigenus 34, which he also manages to construct explicitly. But then what he does is the following. So he observes that if you can construct 2 such surfaces, so for instance, sigma genus 1 and sigma genus 2, then you can also construct the surface of the sum of these genera in 1 cube higher. The idea how to do this is actually very simple. So you take this surface of genus G1 and surface of genus G2, and then you know that the symmetry group of the cube acts transitively on the faces. So if you fix one face on one side, then you can achieve that on the other side. You will have one face in the same position, and then you build a tunnel between them. So this is how he constructs it. Same idea for the non-orientable case. But as you can see, so summing them together requires you to go in a different cube because you're doing it in 2 parallel copies of the cube. Okay. The other construction that he has is sort of a duplication construction of some sort. So if you can have, if you have a surface of genus G or non-orientable of demigenus K, and you can embed it in the D-1 cube, so then you can sort of take 2 parallel copies of that surface. And then whenever you have some collection of disjoint faces, you can build tunnels between each pair of such faces, which increases the genus by 1 or demigenus by 2. And that's how he shows that whenever you have m such disjoint squares, then for any r from 1 to m, you can realize all of these genera in between. So you get 2g plus r minus 1 for all of these r. And as it turns out, these intervals of genera are long enough that they cover everything he's interested in. So he basically then puts all of these ingredients together and gets all the demigenera that he needs. So this is basically the end of the proof. I think the reason he was interested in this was I believe he was coming from a more graph theoretical perspective, and people were interested how to compute non-orientable genus of a cube graph and things like that. And then he gets that as a corollary to this construction. Okay. Now we would like to sort of improve upon these results in some way by also trying to consider the F vectors. So addressing the second question, what can we do about vertex minimality? And in order to do this, first we make an sort of elementary observation that's maybe a bit more challenging than it looks at first glance. So there's this nice result that is sort of the basis of mod2 intersection theory. If you have two smooth manifolds with these kind of properties that intersect transversely, then the number of intersections has to be even. So this result is true regardless of orientability. But we're not interested in this result. We're interested in its corollary. So as it turns out, so we were looking at all of these cubical realizations that we were getting, and we noticed that sort of every single one of them had an even number of faces. And then this lemma actually gave a conceptual explanation for this fact. So because what you can do is, so you can realize this closed surface in this cube, then this means it's also embedded in RD for that dimension. And then what you do is you want to count sort of the number of parallel faces. So you take Sij to be the number of faces that have stars in this star notation in positions I and j. So that determines one direction sort of in the space. So you take all of these possible parallel faces and you want to show that there's evenly many of them. And what you do then is you slightly smoothen this surface. And then you can intersect all of these faces in this parallel direction by this hyperplane defined there, it's H. And you can sort of immediately see that the number of faces with stars in position I and j is exactly equal to the number of intersections of this surface with this hyperplane. So then by applying this mod2 intersection theory result, you immediately get that this number Sij is even. And then summing over all I and j, you get the number of all faces, so evenly many faces. Okay, so we have the first abstraction now. So this in particular by the F vector that I showed you before means that odd demigenous surfaces will always require an odd number of vertices, and even demigenous surfaces will always require an even number of vertices. Okay, so the other sort of abstraction that we get is from the fact that the graph of the surface has to be a subgraph of a cube graph. So for cube graphs, the result of realizability is sort of a bit more complicated than for all graphs. So when you have general graphs, the sort of the only obstruction is that the number of vertices is, so the number of edges cannot be more than the number of edges in a complete graph. If you want to realize some graph on a particular number of vertices. But here for cubical graphs, there's this sort of complicated W function that characterizes them. So if you define W of n to be the number of ones in the binary expansion of n, and big W to be the sum of all of these, so basically the number of ones you get in all binary expansions of numbers up to n counted together, then it turns out that this W function, okay, for example, yeah, you calculate it like this. So then it turns out that this W function actually provides a bound on the number of edges you can get on this number of vertices. So this is an old result of Gary and Graham. So this is Ronald Graham, the famous graph theory guy, combinatorialist. So yeah, and they showed that this bound holds. So the highest possible number of edges is determined by the W function of this thing. So this is sort of a better bound than what you would get by just saying, aha, okay, it embeds in the D cube, so it must have less than D times 2 to the D minus 1 edges, because it also takes into account that the number of vertices is not necessarily complete. Yeah. So that's the added value here. And asymptotics. I think it has, let me think. Yeah, we looked at this and it has something to do with logarithms, but I don't remember the exact formula. Probably it grows like the logarithm of D somehow. No? I think so. Superlinear? Let's see. Yeah, I would have to think about it. I mean, we can discuss it later. I have it written down somewhere, but yeah, if I look for it now, okay. Maybe the other one is logarithmic, and then you're basically summing n logarithms. Might be something like that. Okay. Right. So because of this result, we can use this W function as sort of an abstraction. So we look at, so we can check if this bound is realized for some specific f vector that we're interested in, and that will tell us if, I mean, if it doesn't hold, then that tells you that that particular f vector cannot be realized as a surface in the cube. For example, surface of genus 5 embeds in Q5 and there is no obstruction, so it all checks out. So for surface of demi genus 10, it actually turns out that it doesn't embed. I will tell you later why not. But it sort of has the same characteristic. So this is not a complete classifier. It doesn't tell you everything. But it's good to show non-existence. So for example, you can show that surface of demi genus 9 cannot be embedded in the 5 cube. Why? Because you know what the f vectors of N9 are. So it's that thing that I wrote there. And then you calculate this W abstraction for all possible F0s, let's say. So for these vertex numbers from 1 to 32. And then you actually realize that the smallest number of smallest value of f0 where this bound is realized is actually f0 is 33, which is more than the number of vertices in the 5 cube. So you immediately get a consequence that this surface cannot be embedded in the 5 cube. So for a while, we thought, okay, maybe the one with the genus 10 can be realized, even though this one cannot. So we already saw that there's some weird thing going on with even versus odd. They seem to behave quite differently. But yeah, for 10, you actually don't have an abstraction. So we had to do more than that to show that it doesn't exist. Okay, so as you can see, this W function is actually has this sort of strange behavior. So it's sort of fractal-like. So this graph here displays sort of the dependence of this maximal theoretically possible genus that you're supposed to be able to get versus the number of vertices. And it sort of looks like this Takagi function. I mean, it reminds me of that. So which is a continuous nowhere differentiable function. It looks like some sort of fractal. Maybe in the limit you would be able to see something like that. Okay. but yeah, if you list all of the possible sort of values where this bound is satisfied, the result looks sort of like this. So notice that here we went, well, up to 42 vertices, which is more than what is possible in the 5 cube, but up to 32 is sort of what you would expect in the 5 cube. There's also some natural cutoff point here, it seems. So the behavior sort of jumps. So it's one of those weird spikes you can see in the graph that I showed you. But conceptually, that's because so once you finish building this 5 cube, let's say, you will not be able to immediately start building more squares, but you sort of add maybe one edge and so on, and yeah, that kind of thing. So it requires some further input to build something again. Okay, anyhow, so the red numbers here are the surfaces that we were able to realize. The blue ones are the ones that satisfy the bound, but nonetheless, we have not been able to realize them. And we also conjecture that they probably do not exist. The other interesting feature sort of this table is that, as you can see, there's some gaps. Because once you can realize a surface on, let's say, V vertices, you can also realize it on V plus 4. So there's this sort of bump construction you can do by sort of extruding an extra cube from a square, and that adds 4 vertices. And if you do it with 2 adjacent squares, then you get 6 extra vertices. So you can always realize every odd number that is at least 4 greater than what you realized. Any even number that is at least 4 greater than what you already have. But that leads to those gaps that you can see there, sort of. So, for example, for the sphere, you can realize it as a boundary of the cube or boundary of 2 cubes, which would give you 20 edges. But then you cannot realize it with 16 edges, so there is no such realization of sphere. Okay. So these are the bounds for orientable surfaces. For non-orientable, the table is a bit bigger because you also have to look at odd demigenera. So basically what you are seeing here is mostly the same for the even demigenera if you divide them by 2 to get the genus, except that the realizability is a bit different. So for instance, here we had this surface of genus 3 that was not realizable with 64 edges, but non-orientable surface on that number of edges does exist. So sort of, I mean, the W function is sort of sharp for the non-orientable case in this example, but not for the orientable case. But there are also cases that are sort of the other way around. Okay. Right. So this thing that we noticed before for N9 can be a little bit generalized. For example, what we showed with this computation that I'm going to show you is that while N6 and N8 can be embedded in the 5 cube already by Schulz, N7 cannot. So indeed, this embeddability is not a monotonic function of the demigenus, but we can also sort of improve the bound that we get for this odd demigenus case, because so you can also take the parity into account when using this W function, and that will give you something extra because the W function of 2 to the D, let's say, is equal to D times 2 to the D minus 1. And then if you kick out one vertex, which you need to do if you have an odd number of vertices allowed, then you will have D vertices, sort of D edges less that you can realize because every vertex is connected, so has D edges coming from it. which means that by removing a single vertex, the bound sort of decreases quite significantly. And actually, what you can do is, so you can then improve the bound by this number that sort of grows like D. So the difference between the bound for the odd and the even dimegenous sort of grows to infinity. So you can see the values in this table here. So in the first column, you have the bounds that you get for even dimegenous, and then the improvement for odd dimegenous is in the second table. Now, by Schultz construction, these bounds for the even dimegenous can all be realized, actually. So those numbers are exact from 6 onwards. But for odd dimegenous, I suspect this bound is not even sharp. So we would need to produce further invariants telling us something in that case. Anyhow, after all of this complicated stuff that we've seen, it's probably fair to ask the question, is it possible to even enumerate the surfaces in the 5 cube? Which would be desirable to do, because on the one hand, it would complete Schultz classification for even dimegenous, but then also it would give us information about minimal F vectors. And as it turns out, yeah, this can be done. So for the 4 cube, you can pretty much enumerate them by brute force, because the 4 cube is not so big. And you get 7 different possible surfaces. Now, okay, maybe I won't show you these numbers, but we actually have 3D models of them. So I was supposed to have, so Erica's student Manuel Esteves is actually 3D printing these models, and he posted them to me, but unfortunately they only arrived on Monday when I was already in Pisa, so I don't have them with me. But yeah, at some point I might be able to show them to some of you live, I suppose. Anyhow, this is what they look like. So these are the possible realizations of the sphere. So this is this beautiful torus that I abstractly represented here. Well, not so abstractly, but anyhow. And actually, you also get some disconnected surface if you're also interested in those. I won't talk so much about disconnected surfaces. They are also possible to classify, at least in the 5 cube. But yeah, so for the 4 cube, it's this one. Okay, now for the 5 cube, brute force doesn't work. We tried it. So we tried extending sort of building surfaces sort of iteratively by adding 1 square at a time and getting all possible things, but the number of them grows very fast. So then we needed some better idea. And I sort of remembered that this guy, Brendan McKay, enumerated all sorts of stuff very fast. So he has this program Naughty, which and Gang, which sort of generate all possible graphs up to isomorphism, up to wherever you're interested. And he uses some sort of automorphism reductions to do this kind of thing. Okay, so I opened up his thesis, and so there's this nice idea there. So let's say we have some collection of objects that we would like to classify up to isomorphism. So what people do, and proved sort of efficient, is to produce some sort of canonical labeling of these objects. This means that so I want to have this kind of function that to each object sort of associates a canonical form. This means that so if the objects are isomorphic if and only if their canonical forms are the same. So then instead of isomorphism, you can just test equality. And C of X always has to be, so the canonical form of the object has to be isomorphic to the object. So that's what they do. Now, it's very easy to produce canonical forms. For example, you can introduce a total order on the set of objects, and then you define this function. So f of x is all objects that are isomorphic to x, and then you define the canonical form as the maximum with respect to this order that you came up with. Unfortunately, this is very inefficient computationally because you have to produce full isomorphism classes. So again, you're basically generating everything. But there's this nice idea. So you can actually improve this significantly by imposing further restrictions, because a lot of the time you won't need to use all possible automorphisms, but you can somehow reduce it. So the idea is to add some constraints. So for example, you only look at all those objects y that are isomorphic to x, but have some extra property. So for example, that their degrees are ordered. So for the cube, sort of the natural thing to take is to say that the vertex should have the maximum possible degree, and then its neighbors should sort of be ordered by degree. And this already fixes an automorphism in some cases, so it's almost the most we can assume. But then you can sort of play with this idea of what a degree is. So you can also define a degree to be the vector of degrees and the degrees of the neighbors, and you have this sort of degree to the power of 2 in some sense, which is more discriminative. So it's better for classification. And yeah, then you can actually compute this kind of thing in practice, because then you can produce one sort of ordered object, and this sequence of degrees will determine what kind of automorphisms you are allowed to consider, because suddenly you cannot just permute vertices freely, but you have to preserve the degree vector. So this reduces the size of the automorphism group and leads to faster computation. So using this idea, we actually get this nice algorithm. So you start with a single square, and then at each step you pick the lexicographically minimal free edge and add squares in all possible ways, and then check if these complexes that you generated by doing this satisfy everything that they need to satisfy. So you are not allowed to get edges of that touch more than 2 squares, because then you wouldn't have a surface anymore. Yeah, so if at some point you run into a closed surface, then you just store it, and then you sort of iterate, and eventually you get all the surfaces and you have nothing more to extend. Okay, so here I was going to show you a live demo of how this works in practice, but I'm going to do it at the end because I have to switch to Python, and then yeah, maybe I don't want to interrupt at this point. But yeah, in a similar way, you can also classify other stuff, surfaces with boundary in the 4-cube. There's many more of those than one might expect. So many more, yeah. So you can see the result here. So we found 2,690 isomorphism classes of closed surfaces in the 5-cube. That's much more than I expected, sort of intuitively in the beginning. And that's more than 6 million individual surfaces. So if you also take their isomorphic copies into account. So huge thing. The minimal F vectors among these are the following. So the computation also showed that there is a realization of the non-orientable surface of the genus 5. This hasn't occurred before. In particular, it doesn't appear in Schultz's paper. But surfaces of the genus 7, 9, and 10 cannot be realized. So that's how we exclude them, basically by brute force. This is also still the best method for triangulations as well. So, I mean, you have to be able to realize stuff too. yeah, it's a sad story. Anyhow, so using this classification for the 5 cube, we can sort of complete Schulz's result for even demigenous. So the complete classification is as follows. So you can realize everything that satisfies this bound, except the Klein bottle cannot be realized in the 4 cube, and the surface of maximal possible demigenous allowed by the bound cannot be realized in the 5 cube. So there is no demigenous 10 surface in the 5 cube. Okay. Now, and well, for odd surfaces, we know what the situation is for the 5 cube, but more generally, odd demigenous is still open. Okay, surfaces with boundary. There's a huge list already for the 4 cube. So you get all of these different topological types. Here I'm denoting them sort of in the usual way. So sigma Gn, for example, means genus G and n boundary components. And then as you can see, if you allow boundary components, you can get to genus up to 2 already in the 4 cube. So yeah, I mean, it's kind of fun. Okay, Manuel, so this doctoral student of Erika that I mentioned, is also producing sort of nice visualizations of the surfaces in the 5 cube. So he's doing some machine learning to find the minimal sort of realization with minimal number of intersections, overlaps, so which you would intuitively think leads to the nicest possible visualization in some sense. He's produced some pretty models of this. Of course, for the projective plane, I mean, that's hard to draw even if you don't do it cubically. I mean, you'd sort of expect some intersection somewhere. Yeah, for the Klein bottle, you get something that sort of you can see in a way. I mean, at least the faces are not covering big parts of it, right? Okay. Then, well, for higher dimensions, we don't know what happens, but we produced some infinite families of such surfaces. So, for instance, that idea of projective plane can also be generalized by sort of increasing the degree of the vertex, and then you get an infinite sequence of projective planes in odd dimensional cubes, which I think is also sort of cute. Okay, so yeah, I'm about to run out of time in about 4 minutes, so maybe I should conclude with a live demo. Okay, and then we can maybe look at the open questions if there's time. Okay, so what does this how does this computation look in practice? Okay, so I coded this in Python. Let me see, where am I? Okay, might be Python 3. Okay, so cubical surfaces. So, I mean, I implemented this for, well, in some version for general dimensions. In one version, which is optimized, it only works for dimensions up to 7 because of the way I'm representing the things. But the basic case is enumeration of closed surfaces in the 5 cube, which is what I'm going to do. And I made it extra convenient. I just need to press C and the enumeration will start. So, and this is what it looks like. So it does an extension at every step and then isomorphism reduction, and then it sort of stores the good complexes, which are the surfaces which are already closed. So it has some So the complexes are the ones that are still remaining, so they have unsaturated edges, and the good complexes are the ones that are already closed surfaces. Okay, so this whole computation takes about, well, last time I tried it, it was about 80 seconds for the 5 cube. The first version I produced took 2 weeks. So yeah, I mean, it's been optimized significantly since then. And so I also have a version of this in Rust, which is significantly faster. So in that case, the whole computation for the 5 cube is over in 3 seconds. And you can also get quite high in the 6 cube with that version. So, but 6 cube is sort of, let's say, on the verge of not doable, because I mean, you would need at least a supercomputer, but even with a supercomputer, I sort of don't think you would get to the end, because in the 6 cube, using this, I got up, okay, it finished. So 2,690 edges, 88 seconds, as I suggested. Okay, sort of, if you do this for the, okay, how do I close this? Okay, good enough. If you do this for the 6 cube, you can get up to 30 faces. And up to 30 faces, you already have 70,000 isomorphism classes of such surfaces. But then the maximum possible number of faces is actually 96. So that's not even halfway. I mean, so 96 is the number of faces in this Coxeter surface. So that is realizable. But there's likely billions of isomorphism classes in the 6 cube. So I did some non-exhaustive computations, and I produced up to 300 million isomorphism classes in some cases. So I would be willing to bet that it's billions is probably an understatement. Okay, so what you could ask is for more theoretical results. Is there a characterization of the F vectors? And if we're dealing with cubes, why not cross polytopes? Something like that. Yeah, so partial enumeration of those was done by Andrea, our other collaborator. Okay, that's all I wanted to say today. So thanks everyone for your attention.
Thank you very much. Questions?
So I wanted to ask something about the computational viewpoint. Do you think that this can be improved by improving the software, or somehow it's only computational power which is lacking? Yeah.
So, well, my suspicion is that if 6 cube is doable, then I would be willing to bet that the 7 cube isn't, even I mean, even if you, I don't know, use all the possible particles in the universe to do the computation, because I mean, it becomes really huge. So for the 6 cube, producing these partial results, in some cases, I was already getting, what was it, maybe 250 gigabytes of data and such, and that was up to 30 faces. So I think, because also the list of complexes that are incomplete increases even faster. So 70,000, the number that we saw, is only the ones that manage to get completed, and they start getting completed somewhere, well, not, which is the first one, maybe around 16 vertices, and then up to 30. So it increases slowly, but then it sort of, I expect it to go faster for a bit, and then go back down. So yeah, just the amount of storage you would need would already be quite big, I think. So yeah. But then again, I haven't actually gotten farther than that, so I cannot say for sure.
Okay, thank you.
Okay.
Any other questions?
So, any idea or thoughts about homological invariance that can give you bounds in this respect, like covering numbers or the sorts?
Yeah, so you mean like in the case of triangulations?
Yes.
Yeah, so actually, yeah, I was considering this idea of trying to define something like a cubical covering type. So I haven't really thought about it that deeply yet. It's something that would be nice to have, but then so sort of what made this nice in the case of triangulations is that in that case you have the Nerf theorem, so it's sort of intimately connected with good covers. Is there a cubical analog of Nerf theorem? I mean, it's not something obvious that I'm aware of, but maybe if you had something like that, there would be ways to make the connection. But yeah, I think something like that would be good to consider. Yeah. I mean, one thing you do have is you can sort of always, whatever you realize, you can sort of split it in two parallel parts. So part in one parallel cube and part in the other. And then you have some sort of Mayer-Vittoris thing going on. And I mean, maybe that gives some information, but yeah, we haven't fully exploited that yet.
Other questions? Right. If not, then let's thank Diane again.
Thanks.
Welcome back. Oops. So I'm told that all of you people drank a lot of coffee. I know I contribute my own share. So that is hopefully to be able to be very alert at the next talk by Claudia Landi, who's going to tell us about tame functors from post sets to chain complexes.
Thank you, Ran, and of course, many thanks to Luigi and Carlo for their kind invitation. It is an honor for me to be talking here, and thank you everyone for attending this talk. The topic today, I'll explain the title later, but is an overview of several works with many collaborators. So the context is that of topological data analysis. Let me give some introduction to this topological data analysis. So the idea is that when one wants to analyze data, very often there are parameter choices. Sometimes these parameter choices are not very well funded, or one doesn't know yet what is the good parameter choice. And so, and also sometimes the structure of the data is better explained by considering a multi-scale parameter choice, and therefore one prefers to consider the various values of the parameters and have a summary of how the data changes under these different choices. So a summary better than a fixed value, a fixed choice of a value. And topological data analysis applies this idea in the following way. When one needs to analyze some data, one builds a parameterized complex. It can be a parameterized simplicial complex, a parameterized chain complex, or a parameterized vector space. And the fact that it is parameterized means that we are studying the data at multiple scales. And from this object, one wants to extract invariants. And these invariants, from these invariants, one should get the information one wishes for explaining the data or the phenomenon under study. So this is the very high level pipeline of topological data analysis. More in detail, what do we mean by parameterized objects? One can model them as functors from a poset category, the parameter space, the indexing category. This can be, for example, the real numbers or the non-negative real numbers, or even products of real numbers. And so we have a poset category that is the set of parameters that we choose. And then we take a functor from this poset category to another category, which could be the one of simplicial complexes, chain complexes, vector spaces. And these are the objects. The functors are the object. And then the morphisms in between two parameterized objects are the natural transformations of these functors. And then TDA is a topological data analysis. So it uses tools from algebraic topology to study these functors, or to move from one family of parameterized objects, for example, parameterized simplicial complexes. We can move from parameterized simplicial complexes to parameterized chain complexes, applying the chain complex functor, or if we apply homology, we land in the category of parameterized vector spaces. And so this is usual algebraic topology. I think my feeling, or I don't know how much it is assured, that it is different. So topological data analysis introduces a new idea to that of the classical one of algebraic topology, is that all these functors that one considers in algebraic topology should be stable. What does it mean? It means that if we perturb a little the data, in our case, for example, if we perturb a little the simplicial complexes, then also the parameterized vector spaces one obtains applying homology to simplicial complexes should only be perturbed a little. So this continuity that the functor needs to satisfy to be useful in data analysis. I think this is the novelty of topological data analysis, because otherwise it is a usual algebraic topology. There is nothing new in that respect. So how to measure the amount of perturbation, how to define continuity? We need to endow these categories with the topology. And the easiest way to do that maybe is defining a metric on those categories. And so using the topology induced by the metric. And one very useful metric is the one called the interleaving distance. This is useful because it it can be defined very general for any functor category that we have considered for many types of parameterized objects. When for both, here it is shown for the case of when the parameter space, parameter category, poset categories are, but it could be Rn, and one could define the interleaving distance in exactly the same way. And the objects can be parameterized vector spaces, or parameterized chain complexes, or parameterized simplicial complexes. And the definition of interleaving distance is always the same. So in the case when the parameter t runs in R, we can take, we have the internal transition morphisms for an object X when we move from the value of X at parameter T to that at parameter T plus epsilon, and then we can also move to X at T plus 2 epsilon, and the same for Y. So X and Y would be isomorphic as parameterized objects if there were maps, all the maps in the category from okay, these are maps in the category. Also here are the natural transformations from X to Y. So we have maps from here to here and from here to here, and composed, they give the identity, and then X and Y would be isomorphic. But to measure how much they are not isomorphic, how much they are different, we look for families of maps that are not natural transformations, because they map things here to things not here but here. And for the family F phi, from here like this, so there is a shifting. And vice versa from Y to X, not directly at the same parameter value, but also here there is a shifting. And then we can check if all these diagrams that we get here commute. So for example, we want this to be the same as this. And of course, in the case when epsilon is 0, this means having an isomorphism. Also, this triangle must be the same as this, and also all these parallelograms should commute. So if all these diagrams commute, and so if we can find the phi and psi such that all these diagrams commute, then we can say that X and Y are epsilon interleaved. And then the interleaving distance is simply the infimum over all these real value, positive, non-negative real values epsilon, such that X and Y are epsilon interleaved. If no such epsilon exists, the interleaving distance actually is an extended metric. It is set to be infinity. I say it is a metric, but actually it's a pseudo metric, because there could be two X and Y which have interleaving distance equal to 0, even if they are not isomorphic. But this is a detail. So in any case, for all these objects here that I want to consider, in those of these functor categories, I can define a distance, the interleaving distance on them, and so I can compare how much how large is a perturbation here in comparison to how large a perturbation is here, and so define continuity. So this is the idea, but as I said, it is not only that we want this stability, but also we want to obtain invariants. And so we wanted to obtain summaries. And the idea for obtaining invariance for an object in this category of functors from Q to C is to decompose, if possible, X into a direct sum of a simple indecomposable. So the hope is that it is possible to do this decomposition, and that this decomposition presents only indecomposables that are simple enough and are of a very limited number of different types, so that we get an easy description. For example, this invariant that was shown here means that we have done something so that the invariants are intervals. And these bars, this is called a barcode, and these bars describe something about this filtration of simplicial complexes and about the data. For example, applying H homology, the green bars count the connected components when they start and when they die along this filtration. And so there is a very long bar that says that at some point this was contains only one connected component. This is H0, this is H1, and this says that when we start from a sample of this data and we parameterize in this way, then we can see that at some points two loops, two cycles appear, and but if we continue filling it in, then they die. And so these bars gives us the two holes here. And so from this information, maybe we are able to say that it is an 8. And so this was possible because in that case it was possible to obtain this simple decomposition of the object into simple indecomposables. So, but if we want to do this in general, this program is successful only in a few, is guaranteed to be successful only in a few cases. For example, when the category, the landing category C is that of vector spaces, and when the parameter space is of Dinking type, like for R, like an A series or a DE series of a poset of Dinking type. So very few cases. Already, if we decide to, sorry, where it is? If we choose as parameter Rn, then that program fails. And that's the basic difference from between one parameter persistence that works very nicely like this, and the multi-parameter persistent, which is this one, where this program here fails because we can't list the simple indecomposables. But in this talk, the landing category will not be the vector spaces, but the chain complexes of non-negative chain complexes of vector spaces over a fixed field F. And whereas Q is not fixed a priori, is any poset category. Here, for illustration, I have chosen Q equals 0 infinity. And so this object can be represented as chain complexes vertically. Each vertical diagram is a sequence of maps is a chain complex. So the composition of two maps, successive maps, is a 0. And whereas horizontally, we have the change of the parameter, and so they are the internal maps of this functor. And so this is the object we are going to study. And so it looks very much like something parameterized by R2, which we know. And we know that for these objects, it is not possible to try to decompose X with a finite family of indecomposable types. So it looks impossible to solve, to carry out our program with these objects. But remember, we have a strong hypothesis that composing the two of these vertical maps, we get a 0. And this changes everything, as we will see. But even if Q is any poset category, we would like, and so it is not necessarily finite in particular, we would like that it behaves as if it were discrete. And so when we say tame functor, we mean a functor that is defined possibly on a non-finite poset, but can be discretized by a finite poset, such that, for example, T0, T1, Tn is a definite poset D inside Q. And what happens is that if we move here between two of these discrete values, then this is going to be an isomorphism. So here we have only isomorphism from here to here, and X may possibly fail to be an isomorphism when we pass through one of these values of D. And there is also a precise way of describing this, saying that X is a tame if it is isomorphic to the left-Can extension of some functor Y defined on a discrete poset along an inclusion alpha of the discretizing poset into, okay, it doesn't even need to be an inclusion. Along a poset map from D to Q, we usually use inclusions actually. But for this talk, it is not important to understand this left-Can extension thing. It's just to say it can be made precise, whatever is a Q. And this is tameness. So tameness is the idea that we can think these functors as discretizable. And now to obtain invariants, so we want to do that on tame functors, not on all functors, only tame functors. But still, there is the problem that, and with the landing category, the chain complexes. But still, there is the problem that not for every Q, it will be possible to decompose X into simple indecomposables. And this will be possible even if we are landing in the chain complex categories in 3 cases that I'm going to illustrate. One is when X is filtered, one is when X is factored, and the poset category is the non-negative reals. And time permitting, also when Q is more in general a poset of dimension 1 and X is cofibrant. So these are 3 cases when it is possible to carry out this decomposition into simple indecomposables. So we started with the filtered case. If I'm too fast, I can skip one of these cases. You tell me, you stop me, you ask me questions, and I don't need to do all the program today. So if I get to the general case, I'll tell you. It means, for example, a tree or a zigzag is a dimension 1. So it means that each element in the poset has no two predecessors or parents, sorry, two parents with the same predecessor. Yes. So in the case when, for example, this is the real, Q is the reals, it is simply that we want to find a finite family of values, parameter values, such that the internal morphism of the object from time at s to parameter value s to parameter value t fails to be an isomorphism only when may fail to be an isomorphism only when there is one of these times in this discrete subset between them. Otherwise, they are isomorphic. And here, the categorical, are you satisfied with this? Do you want the categorical interpret the categorical one? Okay, the categorical one is that X is tame if it is isomorphic to this left-hand extension along a poset map from alpha to Q. So which means that if we can find a discrete set or finite set D that, for example, includes into Q, and we can find a functor y from the discrete poset to our landing category, such that when we take the left-hand extension, which is this one, which is the minimal functor that makes this diagram commute, and if our X is isomorphic to this one, which is the left-hand extension, then we say that X is tame. Sorry, I was very fast because, well, maybe because I needed to have a shorter talk or more time. Okay, sorry. The filtered case. So when we say filtered, we just mean that when we pass from a parameter value S with the transition morphism, internal morphism of X from S to T, the morphism need to be a monomorphism, which means that it is degree-wise injective in the chain complex. It is degree-wise injective. And for example, one can obtain this kind of chain complex if one builds a family of simplicial complexes which is nested, meaning that one simplicial complex is a subcomplex of the following one. For example, using the Vietoris-Rips construction or Čech construction, and so growing balls, disks around the data with increasing radius and taking, for example, the nerve of the covering one obtains. So this is one way, for example, of obtaining this nested family of simplicial complexes, but we are not interested in them. We are interested in what we get when we apply chain complex to this. In that case, we obtain this filtered chain complex. Here, one can study what are the indecomposables for filtered chain complexes. So first of all, what are the indecomposables for a chain complex, not a filtered one? So we only have two types of indecomposables for a chain complex. The one which is called a sphere, which means that it has the reduced homology of a sphere. So it is everywhere zero, and it is the field in a certain degree. or the ones that we call the disks, in the sense because their homology is reduced homology is trivial, and so they look like they are zero everywhere except to consecutive degrees where the map between them is the identity, and here is a vector space of dimension 1. Now, these are the well-known indecomposable for chain complexes. Now, what are the types of indecomposables for filtered chain complexes? One can start from 0 at some time t until one gets, this includes into something that starts being a sphere at a time b. And if we continue at some point, this includes into may include into a disk at a time d. And so it looks like this. And this can be recorded, for example, as a point in this diagram where we recorded the birth time b and the death time d. So homology starts here and ends here. This is one type, and this can be seen as an interval that starts in degree n, dimension n, that starts at b and ends at d. But we can also have something that starts as a sphere and remains as a sphere forever. And this can be recorded as something that is born at b and lasts forever till infinity. And this is another indecomposable. And another one is when we have something that starts immediately as a disk and it remains a disk forever. And this can be represented as a point whose homology is born and dies immediately at the same time. So a point on this diagonal. These are then the decomposables. So for example, to have a complete picture, a sphere is born here, then it continues as a sphere until it becomes a disk, and then it remains a disk forever. So these are the types, or it remains a sphere forever, or it starts as a disk and it remains a disk forever. These are the types of indecomposables, and the result is that even if filtered chain complexes look like two parameterized vector spaces, they are decomposable in this simple way, thanks to the fact that we have a chain complex vertically and we have inclusions horizontally, and so we have our indecomposables. Simple indecomposables and the decomposition theorem, and so the decomposition of filtered chain complexes looks like this. But usually we are not interested in them. We are interested in what one gets, so direct sums of these guys, but we are usually interested in what one obtains when we apply homology to this. And when we apply homology, all the disks become 0, and so we are left only with a bar. And this is the decomposition of parameterized vector spaces that I have shown at the beginning, which gives the barcode. This is this barcode. The direct sum of those bars is what we had here. Only that with chain complexes, we consider all the degrees at once, not one by one. This decomposition is of a filtered chain complexes is basically what all persistence algorithms do, like RIPSer, for example, or does this decomposition of filtered chain complexes. It is hidden there. Nobody really decomposes the parameterized vector space, and it is simply, they are Gaussian operations. operations. So one uses row operations on the boundary matrix. And and applying and in this way we obtain the persistence barcode in TDA. Now, it is not a surprise that if it worked when the internal maps were inclusions, monomorphisms, it also works when the internal maps are epimorphisms. This is called the factored case, and we call these parameterized chain complexes, we call them factored chain complexes. So the idea is the same. At each time we have a chain complex, they are connected by internal morphisms that are epimorphisms. And it is not a surprise that, okay, and again, the parameter space is the non-negative reals. And it is not a surprise that, again, we can describe the indecomposables of these objects as intervals, only that this time these indecomposables, they may start as a disk, remain disks for some time. At some point, they become spheres, and they remain spheres for some time, and then they become completely trivial. So we record, well, they start at 0 as disks, then they continue as disks until time s, and then they become 0 at a time t. And so they are intervals between 0 and t, but with a distinguished value s in between, which can be equal to 0 or it can be equal to t. So what is an application for these factored chain complexes? For filtered chain complexes, the application was the usual one for persistence. For factored chain complexes, our application is that of studying vector fields. So one would like the data to study is a vector field, which is gradient-like, so it has no closed orbits, and it is also Morse-Smale, we will see. And then we can associate to it a weighted-based Morse complex. I will explain. So in any case, we pass from a vector field to a chain complex. Then we can parameterize the chain complex, obtaining a factored chain complex. And now we can decompose the factored chain complexes and get invariants for the vector fields in the form of tagged barcodes. This is the program I want to carry out in the next slides for factored as an application of a factored chain complexes. So we start, what vector fields are we going to consider? We are on a closed manifold. The vector fields need to be gradient-like, which means that they do not present closed orbits, but at the same time, they are not guaranteed to be gradients of some functions. I mean, we don't know that they are gradients of some functions. There exist some functions for which they are gradients, but we don't want to choose one because otherwise the construction will not be canonical for the vector field. And also we need some genericity condition, which is being Morse-Smale, which guarantees that the vector fields can be depicted in this way. So there are only finitely many because we are on a compact manifold singularities. They are rest points. This is the example of a torus where we only have sinks where all the flows converge. We only have sources from which all the red ones are sources from which the flows depart, and saddles. And the fact that they are hyperbolic singularities guarantees us that we have only these kinds of singularities, rest points, and also that the stable and unstable manifolds of these singularities are transversal, so we can connect and so, for example, the unstable manifold of a maximum intersects the stable manifold of a saddle along a flow line connecting the source with the saddle, and analogously from a saddle to a sink, we have a flow connecting them, but we can't have any flow connecting a source and a sink because of this transversality. Or we can't have we can't have a flow connecting two saddles because of this transversality. And this transversality, this fact that it is Morse-Smale and it has no closed orbits, guarantees that we can build a chain complex, which is called the Morse complex, or Morse-Smale complex, or Floor-Morse complex, or Witten-Floor-Morse-Smale complex. Everyone calls it depending on how many people you want to credit for this. But let's say that basically, for example, if in this chain complex, the vector spaces in each degree are generated by the fixed rest points, singular points of the vector field for that index. So, for example, sources on a surface generate each source generates gives us one basis element in degree 2 because the source has index 2. Each saddle gives us one basis element in degree 1 because it has index 1 on a surface, and each sinks gives us a basis element in degree 0. So these are the vector spaces of the chain complex, and the boundary maps which needs to square to 0 are defined in this way. We simply count how many given two basis elements, for example, a source, a chosen source and a chosen saddle, we count how many flow lines we find between them that connect them. And for example, we can count modulo 2. In this case, we obtain this boundary matrix. And so this is counting the flow lines between singular points of a adjacent index. And so we get a chain complex this way, but we are interested in parameterize the chain complex. So how to parameterize a chain complex? One way is the following. First of all, if we don't only have the chain complex, but we also have a choice of a basis, of an ordered basis, and which in our case, the basis is given by the singular points. So in this case, we have the chosen basis because they are the singular points of the vector fields. And also we have weights between two basis elements of adjacent index. And these weights need to be non-negative. Then we call it a weight-based chain complex. And this choice of weights is generic if the weights are pairwise different. So when we are in this situation that we have this generic weighted based chain complex, we can build a factored chain complex by a simplification method. So in our case, for a vector field, we have the basis, which is the singular points, but also we can imagine the weights. And there are different choices. It could be the length of the flow connecting them. It could be the maximum norm of the vector field along them. It could be, but of all these choices, the only one that we have devised as useful for our construction, and we are not saying that there don't exist other constructions that allow you to choose different weights, but the only way we have managed to carry out our program is defining the weight between two singular points as their distance in the Riemannian metric on the manifold. So we are not looking at if at the flow. It could be very long, it could be very steep, the flow very fast or very slow. We are not looking at that. We are only looking at the distance between the singular points. So in the end, I didn't say this is the chain complex here is a is an invariant of vector fields up to topological equivalence of vector fields. And so also our construction in a way will be an invariant up to topological equivalence of vector fields. So how to build a factored chain complex now? There are different constructions. Here I'm presenting only one. We start defining it as the zero chain complex, and then we look at the pair of basis elements with the smallest weight, and such that B is in the boundary of A. So for this pair, which has the smallest weight, and B is in the boundary of A, which means that in the boundary matrix, the column of A is non-zero at row B. We operate a simplification, which means that we update the initialized chain complex with adding this interval chain complex, which starts as a disk and remains a disk until the time given by the weight. And then we simplify the chain complex by quotienting out A and the boundary of A. We update the basis and the weights accordingly, and then we repeat from step 2, choosing another pair with the smallest weight. And so we are adding up these in the composables that are all factored. And then we are eliminating all the pairs of singular points that do not contribute to the homology of the manifold, but are really there only for because of the vector fields is like that. And then we remain with something which is not completely zero after all this quotienting of C, because something cannot be simplified, because the Morse complex gives the homology of the manifold. And so we need to remain with some things that tell us about the homology of the manifold. And these are identified as factored chain complexes that starts as spheres and they remain spheres forever. So if for this vector field here, if we carry out this construction, we obtain this barcode where the infinite lines are the infinite spheres. So they give the homology of the torus. So we have one here, 2 in degree 2, 1 in degree 2, and 2 in degree 1, and 1 in degree 0. And they are not interesting to us because we don't want to study the manifold. The point is we want to study the vector field. So the vector field, this vector field also has this disk that starts at 0 and remains until time 1, and this other disk here that starts here and remains until time 1.8, say. And these two bars that are thick because they are not spheres, they are disk, so they are concentrated in 2 degrees, not only 1. They are the invariant for the vector field. We can prove stability. So we can prove that when we take a smooth gradient-like Morse-Smale vector field to its tagged barcode, that is continuous. And in the case when it is not only gradient-like, but we actually know that it is a gradient, so we know the function that gives that whose gradient gives that vector field, then we can define weights, not taking distances between points, but taking the absolute value of the difference of the function. And in that case, our barcode becomes our map, taking the vector field, gradient vector field to the barcode, tagged barcode, is even 1 Lipschitz. When the vector field, but usually in applications, one doesn't work with the smooth vector fields because one doesn't know them. Maybe one has approximations of vector fields. And so, for example, one has things like this. So if one approximates a smooth vector field by a discrete vector field, one can still build the Morse complex. And now the question is how likely is that the barcode and then we can factor this chain complex and compute the barcode for this vector field. And now it is how likely that is that this barcode we obtain from here is closer to the barcode we would obtain from here. And here the result is that maybe from application is not completely satisfactory because we have not a construction, but we can say this, that given this smooth vector field, there exists a triangulation of the manifold with a discrete vector field on it, such that if we subdivide sufficiently many times this vector field, then this approximation can be good as much as we want. So the two barcodes we obtain will be as close as we wish, provided that we subdivide sufficiently many times. So we have an approximation result. And so this shows that factored chain complexes, as much as filtered chain complexes are usually employed to describe functions, sublevel sets of functions, factored chain complexes can be used to describe vector fields. And this is the message here. And the general case, I don't know. So let's assume we are completely, so we have functors from a poset category to chain complexes over vector fields, always non-negative chain complexes of a vector field. Okay, what one knows is that this is an abelian category, but we don't want to work with this. We want to work with tame functors. And in general, this is not even an abelian category. And also, when one deals with the chain complexes, very well studied classic tool is that of considering a model structure on the functor category, on the chain complex category. So one would like to have a model structure on the functor category, and in general, this is not possible, is not known at least when the poset is not finite. And we don't want the poset to be finite because we want to study stability. So we have the parameter needs to change continuously. And tameness also is a problem for both for having the abelian and the model structure. But there are some choices of Q that solve the issues. And so we can actually have an abelian and model structure on tame. And the choice is that, going back to Ran's question, of using one-dimensional posets. So if we restrict to posets of dimension 1, which means that, that if we take an element in the poset, either its downset is empty, or whenever we have two non-comparable elements whose least upper bound is x, then they do not have a common lower bound. And examples of posets of dimension 1 are the trees. This is also of dimension 1 because we have a direction with the poset, so we don't have a cycle here. And so the predecessor of this is these two, and these two do not have a common predecessor. And also zigzags are examples. So if the poset is of dimension 1, we can say something. But again, we don't want to work with finite posets. So we say, look, you can choose posets that are realization of posets of dimension 1, which means that intuitively you attach an interval between two elements of the poset that are consecutive. Practically, you have a construction, but in any case, now this tree is not like this one, which was a discrete, and it was only a discrete, a finite poset. Now this is an infinite poset. We also have all these points here. This is again of dimension 1, and hereafter we are considering Q as the realization of some poset of dimension 1. So what can we say in this case? Well, we are not so lucky as if we could take an object here and decompose it into simple pieces. We first have to approximate X. And one way for approximating X comes from the theory of model structures, of model categories. And so one way is to approximate X by its minimal cofibrant replacement. The minimal cofibrant replacement, if it exists for Y, for X, if it exists, is unique. It is not guaranteed to exist, but thanks to the fact that Q is of dimension 1, we can prove that it exists, and we can also characterize it. So Y is the minimal cofibrant replacement of X, if and only if Y it must be free in each degree. So remember that point-wise, Y is a chain complex, so we can consider degree-wise. It is a vector, parameterized vector space, and it needs to be free, degree-wise. Point-wise, the map, there must be a map phi from Y to X, which is point-wise minimal and a quasi-isomorphism. This means that the homology of Y is isomorphic to the homology of X. pointwise. And also, this phi must be an epimorphism at each positive degree. So it is like a cover, y is like a cover of x, because here we have an epimorphism in each positive degree. It maintains the same homology of x. It is minimal, so there are no extra things. But also, it is free in each degree, and this makes it easier to study it. So, but for its existence, we need the Q to be of degree 1. There are other assumptions studied by by some collaborators of mine that also gives you this property for Q not of degree 1 of dimension 1, but I will not go on into that. So if we have so now the problem is that not of decomposing X, but decomposing Y, the minimal cofibrant replacement. And the cofibrant objects can be decomposed into a direct sum of indecomposables. And what is interesting is that each summand is degree-wise free and non-zero in at most 2 consecutive degrees. So it is concentrated in only 2 consecutive degrees. In particular, the acyclic summands are like, oh, now the field is K. They start at some point X as KK with the identity, and then they continue like a disk for in the upset of X. Whereas the non-acyclic summand, first of all, their homology is non-trivial only in 1 degree. And in that case, this homology is an indecomposable as a vector space, parameterized vector space. And so one can prove that Y is isomorphic to something that looks like this. We take the minimal free resolution of the homology of Y, which is guaranteed to be of length 1, thanks to the fact that Q has dimension 1. So now P1, P0 can be considered as a parameterized chain complex, and this is exactly the non-acyclic summand Y. So this is Y. So we have a complete description of these summands for the cofibrant replacements. Now, we used the fact that Q is of dimension 1 many times. For example, even for proving the length of this minimal free resolution. And now one thinks, well, what if Q is of dimension 2? Is it possible that the minimal free resolution is of length not 1 but 2, and maybe the indecomposable are concentrated not in 2 consecutive degrees but in 3 consecutive degrees? Well, that was our hope, of course, but it is false, of course. In fact, we have a counterexample with that I'm not going to describe because I'm already late. So, but it is an example of something which is 2-dimensional. It is indecomposable, but it is non-trivial in, it is also cofibrant, but it is non-trivial in 3 degrees, but it can also be extended to have it non-trivial in more than 3. And so basically, this is the output of many work, so I'm sorry if I gave you so many information. You can find the one you are interested in these papers. But the message I wanted to give is that whereas multi-parameter persistence or having is not feasible if you want to do that using the compositions within the composables. Parameterized chain complexes are feasible. The composition of parameterized chain complexes are feasible, and they are a source of invariance for TDA. This is what I wanted to transmit. Thank you.
Thank you very much. Are there any questions?
Yeah, my question is somewhat vague, but I wanted to know, is there a general framework to prove that a complex splits into indecomposable, or you do it basically case by case?
No, you can use the fact that if you find in an object that it includes and also is a it includes, so if you find a sub-object that includes and also projects so that the composition is the identity, you can say that that is a summand for the object you are studying. And so in both the filtered case and the factored case, we have studied what are the possible inclusions, knowing that we only have a chain complex. We know that the composition of chain complex, only spheres and disks. And so what are the possible inclusions? What are the possible projections? And so, yes, that's the tool, basically.
Any other questions?
This is a clarification question. So in your definition of tameness, if you take the homology of the complex, do you get, how does it compare to the tameness that you get for like the persistence modules?
Okay, yeah, tameness is a very abused word. So, for example, here, usually in persistence, tameness means the same as I am saying here, plus the fact that the vector field, the vector spaces are finite dimensional. Okay. Then but here we are not requiring that. And in fact, I'm not saying that the direct sum is finite, but of course, if it is finite, it is.
Any other questions?
I didn't get the part. Could you describe what does it mean for a poset to have dimension 2, 3, or n? I mean, I got the
Yes.
1, but
Okay, that's I can say what it does mean not being one, because then there is a paper by Francesca Tombari and Wojciech Kakowski and Alvin Jean, I think. It's so just to show you the name of these people so that you maybe can find. So Francesca Tombari, Wojciech Kakowski, and Alvin Jean have a paper more in general on posets, where they studied they defined the dimension in general for a poset. So this definition for dimension 1 was the simplified one, so that it was easy to, and I'm sorry, I wouldn't adventure in giving you the general definition, but I just want to say that, for example, some of the results that I gave, like it is possible to endow the set of functors with a model structure, they give it for posets not under the assumption that they are of dimension 1, but under the assumption that the poset is an upper semilattice. So you can devise different conditions that also allow you to do some of this. We focused only on dimension 1.
Okay, thanks.
So sorry.
And this was
I refer you to a paper of Francesca.
Thanks. And this was crucial to have these short
It was-
resolutions of
Yes,
length.
it was crucial
okay.
many times. Yes, also, yeah.
And it is my pleasure to introduce Sandstone, Sun and Blitze, who's going to talk about a combinatorial definition of the string topology product.
I thank the organizers for invitation me, as I am first time in Italy and in particular in Pisa. So, the string topology product originally was defined by Chas and Sullivan, and as minus degree 1 for n-dimensional manifold, closed triangulate manifold, as yes, this minus degree product. And there was a raised question how this product is related with the standard coproduct, which is defined for, they defined for free loop space. Lambda m is a continuous map from cycle to M. And the coproduct is for any topological space is defined, and in particular for free loop space. And how these two products are related to each other. And the question was how these two products are related to each other. Something algebra connection must be. So for this, we defined a new product. This is a 0 degree IG is I plus G degree preserving product. And to do this, we have first to revise this product. Here is I denote this product double cap product by double cap by combinatorially. And also we have to revise the standard Poincare Lefschetz intersection product on itself on M on the chain level. On homology, all are the same, all products. So final answer is this theorem. There is two diagrams that they are commutative. This is a new circled product, and these two diagrams differs by this tensor Samatar interchange. There is this right, here is this product left. So, and this is final answer. Now the question is how this product is defined and how this product is on chain level defined. It is circled by this product on the chain level. This is my question. So this is purely combinatorially is done. So first recall the well-known fact, this is diagonal of the cube. So this is n-dimensional cubes in n letters, and this is a Cartesian product, and let Tn denote the set of ordered partition of this set. And the bar P is with union with these two terms, extreme terms, okay? and then denote phase operator epsilon is either 0 or 1 when it's put in ice position, okay? And when IB is such partition, then consider B this composition is 0 phase operators, and upper one means this, and the upper one means composition of this D1, and then the diagonal of is expressed geometrically as union of such Cartesian products here. And when AB runs over this all for all AB. Okay, and this has two primitive terms, extreme terms, 0 and 0 empty on this one, and second is n multiplied by maximal or maximal vertex of cube. So now this used to construct combinatorial models of both. This means based loop space, and this is free loop space. Okay, and this is about arbitrary cubical set. Cubical set is like simple selection. This is abstractly defined, and but here is two type of operators: D0, D1, and degenerate operators. And these relations between them are as in standard cube. The relations I have also mentioned. To put 0 in position and to put 1 in position, these relations are combined by abstract definition. And with this head means that when simply connected is X, then head can be removed. That means when fundamental group is non-zero, then is this construction. And there is inclusion in this projection such that there is geometrically, when realization you take, then it is a quasi-fibration. Quasi-fibration means that it is not in general vibration, but has the mind properties that induce long exact sequence in homotopy groups. And this is useful to compare two spaces to each other. And the theorem 2 tells us when this is realization, Y denotes realization of X, and this is a vibration, standard vibration. This map var rho is that when you take continuous map from circle to Y, you restrict to fixed point and obtain element this. So this is vibration with fiber, it is based loops. And this combinatorial defined things, I explained below how this is defined. This is a strictly commutative diagram. So vibration can be combinatorially replaced by this quasi-vibration. Okay. Now explicit constructions of het omega het lambda x. This means that we owe two cubical sets interval, one-dimensional interval is regarded with two canonical orientations. Yes, what you see, and this is already needed when fundamental group is non-zero. For when it is 0, this can be ignored, this construction. And what then consider this positively generated cubes and shift dimension, the suspension, and this is bar X. And by bar X, we construct a free monoid. every given any set, we can construct a free monoid with generators. Now generators are cubes, and these cubes are used to define phase operators. Then prime is the minimum sigma 1 is this equalities must be this the dimension. This means the dimension of this must be n, and so on. And then there is a factor prime by the degeneracy elements. So this is not important at this first reading. And important is essential the phase operator, how is defined. This depends for partitions A, B. And this is so when in bicubical decomposition, yeah, cubical components, you see. Now this point is denotes multiplication in monoid, in free monoid. So given this is defined on generators and extended multiplicatively for all monoms. X bar is when you take this P 0 and 1 when AB is any partition in Pn, okay? And then second, what is lambda prime? Now omega 2 prime is omega, defined it just omega prime, but to remove these equations, because by definition here, by lambda, we need another condition. This is maximum X is maximum sigma K here, and the maximum X minimum sigma 1 of these two relation qualities. Then also this is prime is by is factored by degeneracy operators, but phase operators now has three types. So, but phase operators is of three types. When this is B0, this belongs to this set, and second is this all are defined by decomposition of initial cubes. You see, here is 0, 1, and here is R0 here, and this is permuted in last place. So this resembles a Hochschild differential. I will say here below about this. In particular, given the cubical complex C star X, the cellular chain complexes, the cellular chain complexes of this omega is identified with cobalt construction. When the fundamental group is 0, hat is removed, and this is standard Adams-Cobalt construction defined for any Dejeku algebra. And in particular, when Dejeku algebra is a chain complex of a cubical set, this defines this construction. This is equality. And also, here is when is removed hat by when simply connected space is X, then this is a standard co-Hochschild complex. So, and then homology is computed from this Hochschild complex, homology of free loop space, and so here. Okay. Now we mention that this is important, and this both this sets, abstract sets admit canonical permutahedral structure. We explain it below, but first we modify, as I mentioned, cubical intersection product combinatorial on level M. And let M is triangulated, and this triangulation canonically defines cubical subdivision denoted by K upper box. And here is written how it's this K prime is barycentric subdivision, and barycentric subdivision, any simplex is standard is defined by string of simplexes that are inclusions. Okay, and then cubical subdivision is obtained. What I sigma tau means cube, which is defined by this formula, which I write in. Where is simplex, and this is two-dimensional, and first we and then cubical subdivision here. What is written? When sigma this and this point tau is here, then this is this cube. By this vertex, this is so. Now triangle is union as union of three cubes. So this is phase operators, how it's defined by eliminate some vertex and here audit some vertex. So each each step is elementary, but are many details to be checked. So all these elementary in textbooks contain it. So and now how is defined this combinatorial intersection product? X is X denotes now K box. This is cubical subdivision of M. So there is by these formulas, but the first one is essential because this is used here and here in other. And what I also this right picture for this. Let M is this table, this plane. Then this is cubical subdivision. Okay. So there is rule how two cubes can be multiplied. So when you multiply this and where is q-dimensional, in this case we obtain for this which dimension is must be plus q minus 2 because this is two-dimensional. M is two-dimensional in this case. And the rule is so first when is, for example, simplest case is when and where by orthogonal complemented by this sum square. Then intersection with B is set theoretical intersection. Coincidence, this is this point. But when, for example, U is two-dimensional, and again this B is one-dimensional, then this product is this one. Always must mention, always the result is in first contains a space, contains in U, and this phase has general general expression is sum A such phase is always. And this Leibniz rule is satisfied. So in homology is defined this. So now when here is the classical, we recall classical intersection product on chain level. This is C CP, K is original triangulation of M. K star is block dissection of K. This is by Poincare simple Poincare cells, and which use by this isomorphism, Poincare isomorphism, and K prime is barycentric, first barycentric subdivision of K. And as these operators, what here is written, and standard on-chain level are denoted by tilde tilde square is product is given by decomposition here. What this and so here is other for M is three distinct different complexes. And now to compare our definition with this is as this diagram. So this is right column is this standard complexes, and this it says by Zoom, and the left hand is cubical subdivision. All is cubical subdivision, and then this product intersection combinatorial is defined so that this diagram is strictly commutative. So you can understand details by comparing these two diagrams to be commutative. And then this product, cycled new product, is defined here as decomposition, but it is written. But to understand the details, what here is what we recall what is permutahedra. Permutahedra is convex full standard definition of n factorial vertices, but it can be and this combinatorially faces of permutahedra is indexed by partition. So, but it can be represented is convenient as a subdivision of the cube. Now here is P2 interval. It is interval as is hexagon by three numbers. How this, and inductively here is four-dimensional, so on. And now is we need diagonal. This is likely as cubical diagonal components and contains such components, but in addition contains more components, of course. And here is delta P, which is cell of some cell of permutahedron, A sigma and B sigma are obtained by formulas. Here is written. Some and for n is equal to 3, all components is here is 8 components is permutahedron. So then finally, this diagram is that their components, their diagonal components defines permutahedra. And this is here is written. This this no, this is orthogonal. One component, this is here, and x0, 1x is here. Only to go without primitive terms. So here this has six primitive, non-primitive terms, and all here is written. This is edges, and this is in blue is points. Dimension is shifted. You see three-dimensional cube and two-dimensional permutahedra hexagon. And another correspondence is this is a free loop spaces, and dimension is preserved. And also here is in addition used primitive terms of cube. You see this is two primitive terms, and here is also used. So, but used two times. For example, this no 0 x 11, and below is reversed x11 no 0 x6. So, and finally note that the identification, what is this identification allows this with Hochschild complex to introduce on Hochschild complex various multiplicative operations that arise from geometry of lambda x. The formulas that express this triangular relation of such can be used to construct analogous operations on the Hochschild complex of coalgebra, which is not necessarily comes from cubical sets. This in particular leads to the notion of loop B algebra C. So this thing I finished.
Thank you. Are there any questions?
Can you please go back to the first theorem?
Okay. This one.
Yeah. So the double circle product was defined to kind of find that relation between the usual this string product like the double cup and the standard coproduct, right?
Yeah, this is a standard coproduct or tensor.
Yeah.
This is tensored by itself. You see, and this is chain 11, but transformed, modified by Sullivan-Charles product. Neo homology is the same, and this is new one. This is degree preserving product.
Okay. Is there is this operation kind of uniquely defined by this commutativity, or there might be other operations which do the same?
So this how is detected this operation by construction? What I will in final see what I did. This is a model of free right hand side. This is model of free loop space. When you this product chain level this double cap product defined, and then define diagonal of this polytope. Also, I will write here. Again, on the chain level and on the geometry, by the same symbol, you mean this is permutahedra, one permutahedra modeling for example, and there is result some phase in Bermuda-hedra, okay? And when they consider where you take a diagonal of Bermuda-hedra, and here also in both factors, you consider this one and this one. So there is interchange these two, and then consider in first this, and the other is uniquely resolved by this. Yeah. So algebraically, this means this is some unique.
Is uniquely determined by the
uniquely,
contraction.
when you this correspondence projection, you consider and then you will see this one.
Thank you.
This one.
Any other questions? Well, if not, then let's thank the speaker again.
Okay, welcome back for the first talk of this afternoon, which will be Paola Cristofori with a PL approach to trisection of four manifold through colored triangulations.
Thank you. And first of all, let me thank the organizers for the invitation to give this talk and participate in this workshop. Okay, I will describe a PL approach to the study of trisection of four manifolds by means of a particular class of triangulations that can be encoded by edge-colored graph. I will show how some problems related to trisections can be translated into this combinatorial setting. In particular, I will define a PL invariant, giving an upper bound for the value of the trisection genus of a closed form and PL4 manifold. And also we will see that an estimation of this invariant can be obtained from a Kirby diagram of the manifold. This is a joint work with Maria Rita Casali, and the work was inspired by a paper by Bell, Haas, Rubinstein, Tillman about trisection supported by triangulations, and by also by a subsequent development due to Spreer and Tillman. Okay, the plan of the talk is as follows. I will briefly recall the definitions of trisection and trisection genus of a smooth closed form manifold. Then I will introduce the trisection induced by a particular class of triangulation, the so-called colored triangulations, or equivalently by their dual graphs, which are called gems. Then I will present some estimations of the trisection genus of a closed smooth form manifold via gems. And finally, I will discuss how to obtain trisection of PL4 manifolds from any gem. So trisection were introduced by Gay and Kirby, have been intensively studied, and has become a useful tool for the study of the topology of smooth form manifolds. They are a four-dimensional analog of Eger splittings of three manifolds. In fact, as a Eger splitting consists of two three-dimensional Handel bodies with a common boundary, a trisection of a closed smooth form manifold is a decomposition of the manifold into three four-dimensional Handel bodies, mutually intersecting into three-dimensional Handel bodies, such that the common intersection is a close connected surface, which is called the central surface of the trisection. Moreover, all Handel bodies and the central surface are orientable if and only if the manifold is orientable. It was proved by Gay and Kirby that any closed smooth form manifold, orientable form manifold, admits a trisection, and this result was more recently extended to non-orientable manifolds by Miller and Naylor. Okay, I think that this figure is a good way to visualize the trisection and can help us to remember the notations I will use. Note that each pair of three-dimensional intersection, three-dimensional Handel bodies, is a Hegel splitting of the boundary of one of the four-dimensional handle bodies. For example, H01 and H12 is a Hegel splitting of the boundary of H1, where the Hegel surface is always sigma the central surface. Moreover, these three Hegel splittings completely determine the trisection. In fact, there is a famous result by Lodenbach and Poenaru for the orientable case, extended to the non-orientable case by Miller and Naylor, stating that any diffeomorphism of the boundary of a four-dimensional handle body extends to its interior. So once we have these three Hegel splittings, there is essentially a unique way to glue the four-dimensional handle bodies to the split according to these three-dimensional manifolds according to their splittings. And of course, each of the Hegel splittings can be encoded by the Hegel diagram. So we have three sets of curves on the central surface. Conversely, a trisection diagram is a four-tuple sigma, alpha, beta, and gamma, where sigma is a close connected surface, and alpha, beta, and gamma are cut system of curves for the surface, such that any two of these systems, together with the surface, is a Hegel diagram of a connected sum of copies of S2 bundles of S1, either orientable, either they are all orientable or they are all non-orientable. As the result I've just cited ensure also that a trisection diagram completely determines a trisection. The common genus of the three-dimensional handle bodies is called the genus of the trisection. And the trisection genus of a closed smooth four manifold is the minimum genus of its trisections. Okay. Just a moment, I forgot. There are important questions related to the trisection genus. For example, it is well known that the trisection genus is sub-additive with respect to the connected sum. Additivity is not known. In all probabilities, is a very, very strong property because it would imply the four-dimensional smooth Poincare conjecture. Moreover, another question that can arise is whether the trisection genus can distinguish different PL structures, structures on the same topological manifold. The answer is generally no. There are counterexamples. There are infinite families of smooth manifolds that are all distinct. They are different, but they are all homeomorphic and they have all the same trisection genus. So a conjecture arose, a conjecture about the questions about is the trisection genus a topological invariant, top invariant? So any two manifolds that are homeomorphic must have the same trisection genus. This is a question. In a probability, very strong questions, because it would imply that there are no exotic structures on the fourth sphere, the smooth Poincare conjecture, the complex projective plane, S2 cross S2, and the connected sums of two complex projective planes. This is still open problems. As we will see, a kind of trisection genus can be defined by using triangulations. And this is a consequence of some results about the study of trisection supported by triangulation. By taking advantage of the by taking advantage of the coincidence between diff and PL categories in dimension 4. This PL approach was started by Bell, Haas, Rubinstein, and Tillman, who presented an algorithm to obtain a trisection from any triangulation of a closed orientable PL manifold. They make use of a labeling of the vertices of each four simplex of the triangulation by three colors. This is called the tricoloring. And under suitable conditions, it determines a trisection. Actually, this condition can always be satisfied by performing Pachner moves on the triangulation, also at the cost of increasing the number of four simplices. Sperry and Tillman applied the idea of Bell-Haas, Rubinstein, and Tillman to a very special class of triangulation, that is colored triangulations with exactly 5 vertices and 10 edges. Okay, so what is a colored triangulation? A colored triangulation, K of a closed PLN manifold, is a pseudo-triangulation. That is a triangulation realized by a pseudo-complex. It is a more general concept than that of simplicial complex, because basically we allowed 2 simplexes of the triangulation to share more than one face. But identification of faces of the same simplex are not allowed. A color triangulation, so it is a pseudo-complex together with a labeling of the vertices of the triangulation by the integer from 0 to n, which is injective on any simplex. Such a triangulation can be efficiently encoded by the one skeleton of its dual complex, which is a regular multigraph. There are multiple edges but no loops, whose edge of degree n+1, whose edges inherits a coloration from the labeling of the vertices of the pseudocomplex. In fact, two vertices of the graph, which are barycenters of 2 n-simplexes of the triangulation, are connected by a C-colored edge if and only if the 2 corresponding n-simplexes share the n-1 face opposite to the C-labeled vertex. We say that gamma is an n+1 colored graph representing the manifold M, or it is a gem of M, where gem means graph encoded manifold. The duality between graph and triangulation establishes a bijective correspondence between the H-simplexes of the triangulation colored by certain colors, say C0, CH, and the connected component of the graph without its C0, CH colored edges. In particular, for each color C, each connected component of the graph without its C-colored edges represents the link of a C-labeled vertex of the triangulation in its first barycentric subdivision. This is called the het C residues of the graph. By this property, we obtain a characterization of gems of closed PLN manifolds, and the condition is that for every color C, each het C residues of the graph represents a PLN-1 sphere. By weakening this condition and allowing the residues to represent not only sphere, but also close-connected PLN-1 manifold, we obtain gems representing singular N manifolds. Polyhedra that, roughly speaking, singularities arise only around vertices. This representation can be easily extended to manifold with non-connected empty boundary by saying that an n+1 colored graph represents a compact PLN manifold N, or is a gem of M, if its dual pseudocomplex is a triangulation of the manifold, a singular manifold, obtained by capping off each boundary component of M by a cone. It is not difficult to prove that any compact PLN manifold can be represented by an n+1 colored graph, which is bipartite if and only if the manifold is orientable, and can always be supposed to be a so-called crystallization, that is, for each color C, the dual triangulation has only one C-colored vertex, or all C-colored vertices of the triangulation are singular. Okay, this representation allows to define PL invariants of the manifolds directly on the graphs. I will focus on one of them, the regular genus, which, as we will see, is strictly related to the trisection genus. Okay, given an n+1 colored graph and the cyclic permutation epsilon of the color set, the regular genus of the graph with respect to this cyclic permutation is defined as the genus of the orientable surface where the graph admits a particular type of embedding called regular, if the graph is bipartite. If the graph is non-bipartite, the regular embedding is into a non-orientable surface, and we consider half the genus. And we can compute the regular genus by means of this very simple formula. By taking the minimum of the regular genera among all cyclic permutations of the core set and all gems of a given competent manifold, we obtain a PL invariant, which is called the regular genus of the compact PL manifold, similarly to what, for example, to the Igar genus in dimension 3. Okay, the regular genus in dimension 2 equals the genus of the surface if the surface is orientable, or half its genus if the surface is non-orientable. And the same way, in dimension 3, the regular genus of a closed 3 manifold equals its regular genus, or half its its Agar genus, or half its Agar genus if the manifold is non-orientable. Well, here you can see an example, a 4-colored graph representing the Poincaré homology sphere, regularly embedding into the closed orientable surface of genus 2, according to this permutation. So the regions of the embedding are disks bounded by bicolored cycles whose colors are consecutive in the permutation. Actually, this embedding is minimal with respect to the genus, since the regular genus of the Poincaré homology sphere is 2. Okay. Compact PL4 manifolds have been classified up to regular genus 1 and up to regular genus 2 in the case of empty or connected boundary. Genus, if the manifold has genus 1, it is a 3-sphere bundle over the swan, a genus 1 and the body, or a product of a closed 3 manifold by of Agar genus 1 by the interval. If the boundary is connected and the genus is 2, we have, apart from connected sum of the above manifolds, the complex of projective plane S2 cross S2, the genus 2 and the bodies, and all the other 2 disk bundles over S1. Or the manifold can be represented by a non-trivial frame knot. That is, it admits handle decomposition with 1, 0 handle, no 1 handles, and 1, exactly 1, 2 handle, represented by the knot. And its boundary, which is the closed 3 manifold obtained by dense surgery of this frame knot, is a length space L alpha beta with alpha greater than 2. Okay. Let's go back to the work of Spreer and Tillman. They consider a particular class of colored triangulation, that is colored triangulation whose one skeleton coincides with the one skeleton of 4 simplex. Their dual graph are called simple crystallization. And by using simple crystallization, Spreer and Tillman obtain minimal trisection for the complex projective plane S2 cross S2 and the K3 surface. As a consequence, they computed the trisection genus of all the so-called, they call them standard simply connected 4 manifolds, that is connected sum of the above manifolds. In all these cases, the trisection genus turns out to coincide with the second Betti number and also with half the regular genus. Unfortunately, not any closed PL4 manifold admits a simple crystallization. For example, the manifold must be simply connected. On the other hand, all possible simple crystallization of a given manifold have the same number of 4 simplices, which is minimal, and depends only on the second Betti number. So, since there are topological manifolds admitting infinitely many different PL structures, there must be infinitely many PL manifolds for manifolds not admitting simple crystallization. And these were our motivation into generalizing Spreer and Tillman's construction so as to include any colored triangulation. So starting from any gem. Well, it was not a very difficult task. It was an easy extension. And it was also, the construction was also easy extendable to the case of manifold with connected boundary or non-orientable manifolds. I will briefly outline this construction. Let us start with the closed case. Let gamma be a gem of a closed PL4 manifold, and epsilon a cyclic permutation of the color set, for example, this permutation. We can always suppose that the triangulation has only one four-level vertex. Otherwise, there are moves, combinatorial moves on the graph, not changing the manifold and reducing the number of four-level vertex. So we can define a tricoloring by giving color red to the 0 and 2 label vertices of the triangulation, color green to the 1 and 3 label vertices, and color blue to the unique 4 label vertex of the triangulation. Then we obtain the composition of the manifold, whose pieces are pullbacks of the cubical structure of this, the standard to simplex, by the natural map induced by the tricoloring. So the map sending all equally colored vertices of the triangulation to the corresponding vertex of the two simplex. H1 and H2, two of these four-dimensional parts, are always handbodies, since they are regular neighborhood of the subcomplexes of K, the triangulation, generated by the red and green vertices respectively. H0 is always a four ball, since it is a regular neighborhood of the unique blue vertex of the triangulation. The three-dimensional intersection H01 and H02 are always handbodies, and the common intersection is a close connected surface. The genus of these two three-dimensional handbodies equals the regular genus of the graph without these four colored edges. Okay, as you can easily see that this construction does not depend on the fact that the manifold is closed. It can be extended easily to the case of a manifold with a connected boundary. In this case, the triangulation is a triangulation of the associated singular manifold. And we can suppose that, the four-label vertex is the unique singular vertex of the triangulation. So the composition is almost the same. The only difference is that H0 is not for ball, but it is the cone of the boundary of the manifold. So by dilating a suitable regular neighborhood of the four-colored vertex, we obtain a decomposition of the manifolds with boundary, the compact manifold, with almost the same pieces, except H0 that now is a color of the boundary of the manifold. This is, in the closed case, this is almost a trisection. The only problem arises from this three-dimensional intersection, the intersection between H1 and H2, which could fail to be a handbody. If this is the case, if H12 is a handbody, we called this decomposition a jam-induced trisection of the manifold. And this is only a summary of the properties that I've just explained. These are the intersection of the three-dimensional pieces of the decomposition, which each four simplex. H01 and H02, this one, are union of these prisms, this prism and this prism. So it is easy to see that they are handbodies, since the union of the prism collapses to the union of the green and red vertices of the prism, respectively. What happens with H12? This is a union of cubes, these cubes. And it is easy to see that the union of these cubes, which is H12, collapses to the union of the bottom faces of the cubes, this blue square in the figure. But a further collapse to a one-dimensional complex is not always guaranteed. However, by using the correspondence between simplexes of a triangulation and subgraphs of the graph gamma, we can establish a condition encoding a possible further collapse to a one-dimensional complex. In fact, each blue square, the bottom faces of the cubes, is dual to a four-colored edge of the graph, and its sides correspond to bicolored cycles of the graph, all involving color 4. And this is a building block of the spine of H12 made by the union of the bottom faces of the cubes. We call it H bar. Okay. A possible collapse of this spine to a one-dimensional complex could be encoded by an ordering of the 4 colored edges of the graph, satisfying this condition. For each edge EJ in the ordering, there is a color I such that all 4 colored edges belonging to the 4 I-colored cycles containing EJ come before EJ in the ordering. In fact, each of the 4 colored edges in this ordering represents the collapse of its dual square, blue square, in the possible collapse of the spine H bar, because if we suppose that at the J step, all the squares corresponding to the 4 colored edges A1, AJ minus 1 have already collapsed, then the square corresponding to EJ has a free face, and this is exactly the face corresponding to the 4 I-colored cycle. So there is a further collapse of the square corresponding to EJ too, and collapse can go on. Okay. Similarly to, let's remember this condition because we are going to use it at the end of the talk. Similarly to the trisection genus, we can define the G trisection genus of a PL compact for manifold with empty or connected boundary as the minimum genus of a jam-induced trisection of the manifold. And of course, if M is closed, the G trisection genus is an upper bound for its trisection genus. For some classes of manifolds, this bound is sharp. For example, if we have a closed for manifold admitting a so-called weak simple crystallization, better. If there is a secret permutation epsilon of the closed set, that's such that this crystallization is weak simple with respect to epsilon, that is, the dual triangulation contains only one simplex between pairs of vertices whose colors are non-consecutive in epsilon. And if this crystallization induced a jam-induced trisection, then it is a minimal once. So the G trisection genus of the manifold coincides with the genus of this trisection. It coincides with the trisection genus of the manifold with its second Betti number, half its regular genus. Well, the major problem at this moment is to see when a jam or a colored triangulation of PL for manifold with empty or complementary boundary induced a trisection, which are the manifolds admitting jam-induced trisection. Okay. A first observation. When a manifold admits a jam-induced trisection, all the alto bodies and the central surface must be orientable if and only if the manifold is orientable. So no closed non-orientable manifold admits a jam-induced trisection. No non-orientable manifolds with an orientable boundary admits a trisection. But moreover, we have another condition. If M admits a jam-induced trisection, then its associated singular manifold must be simply connected. This is because one of the 4-dimensional parts of the trisection is always contractible. It is the four-ball, the closed case, or the cone of the boundary, and its fundamental group surjects onto the fundamental group of the manifold. Actually, for closed, simply connected for manifold, closed, simple connector is necessary. For manifold, we have a complete characterization of manifold admitting a jam-induced trisection. They are precisely the manifold which admits trisection where one of the 4-dimensional handle bodies is a four-ball, And these are precisely the four manifold admitting handle decompositions with no one handles or no three handles. This class could contain all simply connected closed PI4 manifolds, according to one of Kirby's problems in his list of problems in low-dimensional topology. But the problem is still open. Oh, at this point, I must recall that there exists a notion of trisection also for manifold with non-empty boundary. It was introduced by Gay and Kirby in the same foundational paper about trisections, and it is quite different from the decomposition we have just seen. In fact, Gay and Kirby's decomposition kind of distributes the boundary among the four-dimensional parts, which are compression bodies, the surface as boundary, the central surface as boundary, and the trisection induces an open book decomposition of the boundary of the manifold. While in our case, a jam-induced trisection have the surface of a central surface is always closed. The boundary of the manifold is contained only in one of the four-dimensional parts, and the trisection induces a Haga splitting of the boundary. Nevertheless, jam-induced trisection of a manifold with non-empty boundary, connected boundary, are not so useless since they allow an indirect approach to trisection of closed PL4 manifold. In fact, if we have a compact 4 manifold, PL4 manifold, whose boundary is a connected sum of S2 bundles over S1, either or orientable or non-orientable, and the manifold admits a jam-induced trisection, then by the results by Laudenbach-Poenaru and Miller-Naylor I have already cited, there is a unique way to glue a handle body to the outer boundary of H0. So what we obtain in this way is the trisection of the closed 4 manifold associated to the compact manifold. And of course, as a consequence, since the central surface is the same, the G trisection genus of the compact manifold is an upper bound for the trisection genus of the closed manifold. We can, yes, actually, we can prove that for any closed PL orientable for manifold, there are trisection arises in this way from jam-induced trisections of the compact 4 manifold, which is the union of 0, 1, and 2 handles in a handle decomposition of the closed manifold. And the basic tool for this proof is the possibility of constructing a jam of a compact 4 manifold, starting from a sufficiently nice Kirby diagram. Kirby diagrams are a commonly used representation from closed PL4 manifolds, encoding handle decompositions. Essentially, a Kirby diagram is a link in the tree sphere where some components are dotted and some components are framed, that is, they are equipped with integers. And this diagram encodes the union of 0, 1, and 2 handles of the decomposition, since each 2 handle is represented by a knot in the tree sphere. The knot is the core of the attaching solid torus of the 2 handle. The tree sphere is, of course, the boundary of the unique 0 handle of the decomposition. And the integer specifies the framing of the attachment of the 2 handle. With regard to the 1 handle, there are different ways to represent them in a diagram. Here we use Akburut's notation. I'm not going to define this notation. It is enough to say that each detachment of each 1 handle is represented by a component of the link, which is unknotted, unlinked from the other component representing 1 handles. and it has no framing. It is marked by a dot to distinguish it from the component coming from the two handles. Actually, this diagram represents only the union of 0, 1, and 2 handles. And the output of the algorithm I'm going to show is precisely a triangulation of the singular manifold associated to this compact manifold, the union of 0, 1, and 2 handles. In particular, if the composition has no 3 handles, this is exactly a triangulation of the manifold. Moreover, if the manifold has a boundary which is a connected sum of S2 bundles of trivial S2 bundle of S1, there is a unique way to attach 3 handles and the unique 4 handle to get a closed manifold. So the closed manifold can be uniquely determined by the diagram and the possible number of 3 handles. I should also recall that the boundary of the compact form manifold represented by a Kirby diagram is a closed 3 manifold obtained by dense surgery on the associated frame link. That is the frame link obtained by substituting each dotted component by a 0 framed one. Okay. The Kirby diagrams we take into consideration have some requirements. They are connected and their dotted components must be in a good position. By a good position, we mean that they are embedded, standard embedded in the plane, like you can see in this figure, and that overcrossing and undercrossing never alternate along them. However, by suitably rearranging the handles of the decomposition and possibly performing some radiomaster moves, we can always suppose that any PL closed orientable for manifold admits a Kirby diagram satisfying these conditions. Okay, so let's start with the construction. The first step is the construction of the gem of the 3 manifold, which is the boundary of the 4 manifold. And as you can see, this graph can be practically drawn over the diagram of the link, as you can see from this example, by substituting the crossing with these subgraphs and by substituting curves with these subgraphs. Why curves? Because the diagram must be self-framed. That is, it is possible that we must add curves to each frame component such that the right of a component equals its framing. For example, this component has rise 2, while its framing is 0, so it needs 2 additional negative curves whose corresponding subgraph is here. While this frame component requires no additional curves since rise and framing are equal. Yeah. Okay. A basic move of the algorithm is the addition of 3 4-colored edges on a particular subgraph, which is called a quadricolor. We can find a quadricolor on the subgraphs, on each subgraph corresponding to a frame component. A quadricolor consists of 4 vertices, satisfy a combinatorial condition, which I'm not going to read, but you can see here. And we can find a quadricolor on each frame component because the quadricolor always arises either between an undercrossing at the curl. So for example, in this case, here is a quadricolor because this is the graph corresponding to this undercrossing. And then we're supposed to add the 2 negative curves here. Here you don't see any quadricolors, but in order to have one, we add 2 opposite curves on this framed component. So, example, we get this graph where there are 1 quadricolor here for this component and 1 quadricolor here for this component. So, If the QB diagram has no dotted components, so the composition has no one handles, this is all we have to know. In fact, in this case, as you can see from this example, after having drawn the four-colored graph representing the boundary on the diagram, this is a trefoil, simply a trefoil, by adding also the curves, because the rise here is 3 and the framing is 0, so we need 2 additional negative curves, which are here. Then we add the four-colored edges, the red ones, by doubling the one-colored edges everywhere, except on the vertices of the quadricolors, where we put the edges as we saw in the former slide. When dotted components appear, the algorithm is more complicated. And it depends on the choice of some points and sequences of segment of arcs on the link. Each choice can produce a different gem, but all these gems represent the same four manifolds. It is the four manifold encoded by the initial Kirby diagram. The choices are as follows. For each dotted component, we choose 2 points, H and H prime, such that I divide the component into 2 parts, one containing only undercrossing and the other containing only overcrossing. On each frame component, we choose, we call it a cut X, point X, between a curl and an undercrossing, or between 2 opposite curls. And we highlight a sequence of consecutive segment of arcs on the diagram without the cuts X. In this example, there are 1, 2, and 3 segments of arcs, such that for all dotted components, the point H and H prime belong to the boundary of the same region of the plane determined by the diagram without the point X and the highlighted segments of arcs. In this example, this region is the union of the gray region with the unbounded ones. Okay? I'm not going into details. It is enough to say that the point X, here is X2 and X2 and X3, simply tell us where are the quadricolors, where are positioned the quadricolors. So where we can add the triple of edges related to quadricolors. Okay. The highlighted sequence of arcs tells us how to connect the endpoints of the one-colored edges, which are parallel to the segment of arcs that are highlighted. For example, this pair of segment of arcs, this pair, and this pair. This is a prescribed way to add these four-colored edges. And then the point H and H prime allows us to identify on each dotted component 4 vertices, P prime, W prime, which will be important and will be connected by 4-colored edges. So we add the remaining 4-colored edges simply by closing the one 4-colored path. And this is, for example, the result for our initial Kirby diagram. This is a 5-colored graph representing the singular manifold, which is a union of 0, 1, and 2 handles of the decomposition encoded by our Kirby diagram. This is the general result. For each choice we have made, the resulting graph is a gem of the represented coupled four manifold. Well, to give a hint of the proof, I will show you that the final result, the final graph, can be obtained from the initial graph representing the boundary and drawn over the diagram of the link, simply by adding 4-colored edges with the precise topological meanings, and performing moves, so combinatorial moves with the precise topological meanings. If we start from the 4-colored graph representing the boundary and perform this move on each quadricolor, so we change the 3 1-colored edges of the quadricolor in this way, we are performing what is called the smoothing of a quadricolor. What is topological meaning? See, in this way, we simply pass from the four-colored graph representing the three manifold obtained by dense surgeries of the link of the frame link L to the four-colored graph representing the closed three manifold obtained by dense surgery on the frame link obtained from L by cancelling the frame component corresponding to this quadricolor. So if we perform the smoothing of all quadricolors, in the link only the dotted components remain, and the resulting four-colored graph represents the connected sum of copies of S1, S2 cross S1, where M is the number of dotted components. By doubling the edges of color 1, we obtained a five-color graph representing the product of this manifold by the interval, and the two boundary components of this manifold are represented, one by the graph without color 1, the one-colored edges, and the other by the graph without the four-colored edges. Now, the attaching of the four-colored edges according to the highlighted sequence of segment of arcs is simply a retriangulation of this boundary component in order to create on the dotted component the so-called row 3 pairs. There are one row 3 pair for each dotted component. A row 3 pair is a pair of four-colored edges sharing exactly 3 bicolored cycles. And the endpoints of these edges are exactly the vertices V, V prime, W, W prime on each of the components that we have identified in the algorithm. The switching of this row 3 pair, that is, we connect V with V prime and W with W prime, in this context can be proved to translate the attaching of 0 and 1 handles on this boundary component, attaching of the gluing of a handle body on this boundary component. While if we put back the one-colored vertices in their original position, we are translating the addition of the two handles of the other boundary component. So the result is precisely the union of 0, 1, and 2 handles by attaching one handle body on one side and the two handles on the other side of this manifold, boundary component of this manifold. Okay. The good news concerning trisection is that for each good Kirby diagram satisfying the initial condition I have just told you, for each good Kirby diagram, the graph obtained in this way by the Kirby from the Kirby diagram always determine a gem-induced trisection, because therefore its four-colored edges can be always ordered according to the condition we have just seen. And the genus of this trisection is precisely S plus 1, where S is the crossing number of our diagram. This comes from the fact that the four-colored graph is practically drawn over the link of the diagram of the link. So if the compact form manifold has a nice boundary sway, this gem determines a trisection of the compact form manifold, but also a trisection of the associated closed manifold obtained by gluing the handle body on the outer boundary of H0 with the same central surface, so with the same genus. So we have an upper bound for the trisection genus of any closed-orientable form manifold in terms of the crossing number of any connected good diagram of the manifold. Moreover, if the diagram has no dotted component, so the manifold admits a handle decomposition with no one handles, the four-colored graph representing the boundary can be manipulated by means of combinatorial moves, not changing the manifold and not interfering with the quadricolors. So as the subsequent addition of the four-colored edges according to the algorithm produces a four-colored graph, again inducing a trisection, whose genus is M alpha, whereas M alpha is the number of alpha colored regions in a chessboard coloration of the diagram, where alpha is the color of the unbounded region. Okay. Unfortunately, these bounds are very far from being sharp, although this estimation is better than the first one, obviously. So in many cases, it is a good idea to start, instead of starting from the Kirby diagram, to start from the composition of a compact, of a closed, let us restrict to the closed case, of a closed PL4 manifold, induced by a gem, which is not a trisection, but has a low genus, and try to modify the composition in order to get a trisection without increasing too much, the genus too much. A way of performing this task was presented recently by Martini and Toriumi, and basically consists into carving regular neighborhoods of the 4 colored edges of the graph. Remember that the graph is embedded in the triangulation as the one skeleton of its dual complex. And then these neighborhoods are carved from H1 and H2 and are added to H0. So what is the result of this operation? It's a kind of stabilization. On the 3-dimensional parts, H01 and H02 remain handbodies, 3-dimensional handbodies, but they increases their genus by 1, and the same happens for the central surface, of course. H1 and H2 are the same. What is changing is how their boundaries are split by the 3-dimensional parts of the decomposition, while one handle is added to H0. So what happens on H12? Essentially, we are deleting 2 handles from H12. In this figure, you can see the effect of performing one of this stabilization by using a 4-colored edge E. It what happens locally around E. More precisely, these are the 2 adjacent cubes of H12. Remember that H12 is a union of cubes. And these are the 2 adjacent cubes corresponding to the edge E. So we have deleted a regular neighborhood here. And the blue square, which is, if you remember, a building block of the 2-dimensional spine H bar of H12. Remember that there is a first collapse of the upper faces of the cubes to the bottom faces, this blue square. And the union of these blue squares we call the H bar. So a hole is created in this square, and so its collapse is assured. So by using at worst all 4 colored edges of the graph, the collapses of all the squares are assured, and so H12 collapses to H bar, and H bar collapses to a 1-dimensional complex. The problem is that we would like to perform the minimum possible number of this operation, because each operation increases the genus of a central surface by 1. And you want to have a low genus, to keep the genus sufficiently low. So it would be very interesting to have an upper bound, at least an upper bound for the number of stabilization that are necessary. And this bounds turns out to be the difference between the regular genus of the graph, with respect to the permutation we used to define the decomposition, and the regular genus of the graph without its 4 colored edges. To give a hint of the proof, which strongly relies on the combinatorics of the graph gamma, we can see it on an example. Let's start from this gem of S2 cross S2. And remember, then if there is a collapse of the two-dimensional spine H bar to a one-dimensional complex, there is an ordering of the 4 colored edges encoding this collapse. At the J step, the square dual to EJ is collapsing from its free face corresponding to the 4I colored cycle. Because all the square corresponding to dual to the preceding 4 colored edges have already collapsed. Of course, the collapse starts if there is in the graph gamma a bicolored cycle of length 2. But if we consider in this example this color, okay, there is no bicolored cycle of length 2 containing an edge of this color. Suppose that this is our color 4. So stabilization are needed to collapse the spine. How can we choose the edge along which perform the stabilization? Okay. Let's consider the graph, the subgraph of gamma, formed by only the 0, 3, and 4 colored edges. It could be disconnected. In the example, is a connected, but no problem. And this graph admits a regular embedding into the two-sphere. The region of the embedding, since it is regular, are the 0, 3, 3, 4, and 0, 4 colored cycles of the graph gamma. Then, let us form a set of 4 colored edges by taking a spanning tree for each component of the graph obtained from gamma 0, 3, 4 by shrinking to a point each 0, 3 colored cycle. Here is the 0, 3 colored cycle. So, for example, we can choose this edge E1 and this edge E2 and perform stabilization along these edges. This means that the blue square of H bar corresponding to these edges have already collapsed. And so, therefore, this determines, the embedding determines an ordering of the remaining 4 colored edges, in this case from E3 through E7, encoding a collapse sequence of H bar after having carved H1, E1, and along E1 and E2. In fact, the square corresponding to E3 now has a free face, since in this cycle, this edge, the square dual to this edge, has collapsed. Then E4, the square dual to E4, has a free face, since this in this cycle, this square has already collapsed, and so on, up to 5. That here we have carved along E2, and this ensures the collapse of the squares dual to E6 and E7, and so the collapse of all the spine H bar. Okay. Now the number of stabilization is K. How can we compute K? It is the number of the edges of the spanning trees that we have chosen. So it is the number difference between the number of 0, 3 color cycles and the number of 0, 3, 4 residues. Here there are some long computations. I'm sparing you. And the result is that this number is precisely the difference between these two regular genera. Now, the genus of the obtained trisection is the sum of the genus of the initial decomposition, which is this number, and this number. So the genus of the obtained trisection is the regular genus of the graph gamma. As a consequence, we have that the regular genus of a compact PL4 manifold is an upper bound for the G trisection genus of the manifold itself. And if the boundary of the manifold is a connected sum of S2 bundles of S1, then the regular genus of M is an upper bound for the trisection genus of the associated the associated closed form manifold. Okay. I think okay, there's no time left, so I'm skipping. This is work in progress, so it can be skipped. And this, thank you for your attention.
Okay. Well, are there any questions? I actually do have one. For instance, the Kirby diagram, or also from the trisection diagram, you can read off some basic invariants for manifold. For instance, the intersection form or something similar. Is it possible to read them off from a gem directly, or is it complicated?
Usually it is complicated. Yes, you have to have nice gems. Yes, but this is one of the problems we have in a list of problems to be faced. Actually, this project have not just started, but is a young project, so we are working on this.
So for now, it's mostly for this trisection related invariant, like the trisection genus.
Yes, because we were interested. Well, we discovered, wow, that the regular genus where we have known for decades was related to this almost new invariant, the trisection genus. And since there are not many information of the trisection genus. Okay. There are examples of computation, but there are very important of the problems I have cited on the trisection genus.
Okay, I have another question from the get-go. Well, Kirby diagrams, but also trisection. Well, trisection much less are kind of related via moves if they represent the same manifold, right? Is there similar theory for gems?
Yeah, there is a complete set of moves, combinatorial moves. They are called dipole moves and bisections. And it was a theorem proved by my colleague Margherita Casali that any two gems of the same PLN manifold can be connected by a finite sequence of these moves, the dimension n. In dimension 3, the set is very small, much restricted, but from dimension 4 higher dimension, we need one moves, one for the move. Yes.
Thank you. Any other questions? No. Then let's thank Paul again. Okay, welcome back for this afternoon session. Now we will have the short talks. And the first one will be Eugenia, which will talk us about equivariant homotopy type of Vettori slip metric thickening of the circle.
Thank you very much for organizing and for this opportunity to speak. So this is joint work with Henry Adams, Michael Moore, Nicola Sadovec, who's here in the audience, and Aditya Saha. I'm somewhat new to these objects, so if I don't know something, probably Nicola knows. If not, then we will send you to Henry Adams or Michael Moore, who are like really pros. Yeah, and I find these objects exciting, so I hope I'll manage to make you excited about them too. So let's recall what a Vittori's complex is, Vittori-Ripps complex is. We have a metric space, and then we have a scale parameter R, and whenever points, whenever a finite subset of points in that space has diameter less than or equal to R, we take it as a simplex. So really, this is an abstract simplicial complex, but when I'm kind of talking about them, I'm talking about when I'm thinking about them, I'm thinking about geometric realization of the spaces. So, and then so here is the depiction, and then you can see here. Well, this is just a graph, but this complex is actually a clique complex. So whenever there is, let's say, 3 edges connecting 3 simplices, then you fill in a face. So whenever there's, say, 4 edges connect, everything is connected to each other, then there is a simplex in there. So that's how basically you can get it from, you can read off the complex from a graph. Okay. And here is the definition of Vittori-Ripps metric thickening. Now you have, this is a space, and instead of, so in a abstract simplicial, in a geometric realization, you have vertices, and then you have, you do like convex combinations of these vertices, and then you get a simplex here. You actually do these combinations on Dirac delta measures. And yeah, pretty much you just kind of substitute vertices for Dirac delta measures. And then, so essentially it's a space of probability measures. And correspondingly, we have a topology on this space that is different from the topology of the geometric realization of a simplicial complex, that original abstract simplicial complex. Rather, well, actually, I'm going to talk about it later. Let's first finish talking about, and then so this picture is supposed to show how one might think, and it's finitely supported. So in this picture, you can kind of, I'm trying to visualize how one might think about distances between points in this measure space, in the space of probability measures, right? So each point carries some mass on it. Let's say I'm talking about thread points. And then you look up, like to measure the distance between, let's say, blue points, you figure out the sort of shortest and easiest way to transport that mass from red points to blue points. And in this case, the blue point, this blue point is closest to these 2 points, so you transfer it, the mass here, and then these guys are kind of connected to each other. This is really hand wavy, but I don't think we really need much about Wasserstein spaces and distances. All right. Okay, so why, we have Vittori-Ripps complexes. Why did people decide to look at Vittori-Ripps metric thickenings? Well, Vittori-Ripps complexes are sufficiently nice. People use them. We know that for example, Hausmann proved in 1995 that when we have a manifold and then there is a sufficiently small scale parameter, Vittori-Ripps complex is homotopy equivalent to that manifold. But the inclusion map is not continuous, for example, right? So that's one downside. Second, well, I mean, I've already noticed that the topology is kind of really different. We have a metric, so if, say, we have some metric space, right? We have a metric in that manifold. But whenever that manifold is yeah, like infinite dimensional, oh, sorry, not infinite dimensional, but not finite, and not finite. And sorry, what I'm trying to say is that it's not like discrete. So for a manifold of dimension greater than or equal to 1, this complex is not metrizable, for example. So there is no way to put a metric on it. Then, oh, sorry, actually there is something missing here. This should be this should be Vittorius-Rips metric thickening over here. So there is a symbol missing. On the other hand, so a nice property of Vittorius-Rips metric thickenings is that this inclusion is continuous. It is also an isometry under its image, and the Hausdorff distance between this original space and Vittorius-Rips metric thickening is at most R for the scale parameter R. Okay. How do they compare? Well, whenever the space X is finite, then they are actually homeomorphic. Whenever, there is a difference, like in my definition there, I said, well, let's consider this sign less than or equal. People also consider the less strict inequality. So in this case, I mean, for Vittorius-Rips metric thickenings, whether you consider less than or equal or strict inequality, they're like very much the same. But for Vittorius-Rips complexes, they could be quite different. But when one considers the open versions, they are weakly homotopy equivalent. Oh, wait. Yeah, that's right. Yeah, so and correspond and so then for example, barcodes that you get in TDA, that would be isomorphic. Yeah, so this should motivate people to study Vittorius-Rips metric thickenings because they are nice, they're descriptive. And so, well, we want to study, if we want to study something infinite, why not to start with the sphere, for example. Yeah, so in Michael Moy proved this theorem. So he found the homotopy types of Vittorius-Rips metric thickenings of a circle, and he proved that they're, well, so for some scale parameters, they are spheres, and then this, a scale parameter grows, the dimension of the sphere grows, right? So here is a picture of that. Yeah. I don't think I want to say anything more about this picture. But the way Michael proved it, he did not consider. Well, there is a group action on this on a sphere. Oh, sorry, on a circle. So circle acts by circle group acts on the circle, and although there was, a strong suspicion that this homotopy equivalence would be equivariant homotopy equivalence, it was not proven by the methods that Michael used. So that's what we did in our project. So here is a definition. This is to describe the action. So, well, we are proving that Vittorius-Rips metric thickening of circle is homotopy equivalent to a sphere, but we need to define the action on that sphere, right? So here is how we define it. Let this subscript denote a circle equipped with the action where whenever I multiply by the group element, I actually, well, so I send it to this power. So then, for example, in this case, the kernel, not the group that stabilizes this would be Z over 2K plus 1. So we have a bunch of these circles, and so we prove that, we you take a join, a circle, and a circle, you get a sphere. And so then, you have a bunch of this. So this is a sphere. And then the action is defined by acting diagonally on this join, right? So, and then, so this scale parameter is really, so we are taking the metric within the circle itself. So whenever you have the scale parameter greater than pi, well, just essentially any point is connected to any point, can be, is within pi distance of any point. So then you get something contractible here. And then, yeah, for smaller scale parameters, you have some finite sphere. Okay, so that's, so we were going to look at this proof, and then some open questions. So the proof. Well, first, let's make an observation. Whenever I have, so I have blue points and red points on the circle, and then I consider maximal arcs containing at least one blue point and no red points. And one can argue by induction that there's always odd number of these blue arcs, maximal blue arcs, right? So that could be sort of refined into observation that this Vittori-Reeves metric thickening at scale parameter R can be, okay, maybe I shouldn't start with that. So whenever I have a measure, all right, maybe just a definition, right? So whenever I have a delta measure, we will define an open interval of length, of this length, centered at this, well, essentially at this point in my Vittori-Reeves metric thickening. So let's say, let's just take an example. Let's take this point. So I take this point and I take, oh wait, this is the opposite one. So I take the opposite point, so that would be the red point, and then I take this interval, right? And then this is essentially all the points that cannot be in, like cannot belong into a particular measure, cannot be in the support of a particular measure, because the scale parameter restricts points points have to be sufficiently close. So whenever this point is in the measure, then this point and all the points over here would not be in that measure. So these red arcs, they then define excluded regions, and then the complement of these red arcs, we have an odd number of these blue arcs then, and so then they are connected components, and they are called mu arcs. And yeah, we have shown that there is always an odd number of them. Okay, so that's an observation. And we use that observation to say that any measure, well, any measure belongs to a particular strata where there is exactly 2k plus 1 mu arcs, right? So I'm given a measure, I can find this blue mu arcs, and then the number of them tells me which strata this measure belongs to. Okay, and the union of all the strata is my Vittori-Reeves metric thickening at this scale parameter. And what happens is, so within each strata, there is a regular polygon, right? So on 2k plus 1 vertices. And what Michael Moy observed, that's like from his original proof, is that one can define a deformation attraction from Vittori-Reeves metric thickening at the scale parameter to some subspace, and that subspace is essentially a union of these polygonal measures. Yeah, and here's a picture of this homotopy. right? So you have 2 points. You just basically move them to like the closest one, closest polygonal measure. It's kind of messy to define it, but the geometric idea is sort of simple. Okay, and so now, so PK is my space of polygonal measures, and you know, if I'm considering things where support, sorry, all the coefficients in the support are non-zero, that will be essentially an interior of a mapping tori. Sorry, I'm kind of, so yeah, so it's sorry, I'm blanking. Anyway, yeah, you get essentially a product of a simplex and an interval, but you have to identify some stuff. So you identify this simplex with itself. And then we take the closure, and that ends up being, so this, whatever I'm depicting here in the picture, this is for 2k plus 1 equal to 3. So this is what we call like mapping torus of polygonal measures. Yeah, and then let's observe that within that space, so the center, all the central measures, they are like this. They form a circle, and yeah, I guess that's all I want to say for now. And then here in this picture, I'm depicting how the S1 acts on points of the polygonal of this 2pk plus 1, this closure of 2pk plus 1, right? So this point is being moved by S1, and in the case 2k plus 1 equal to 3. So the Z3 acts by moving this point here, and this point is identified with this point. So then, yeah, so essentially, but in the center is actually being fixed by Z3. Okay. Now, we also observe that any point in this mapping torus can be written as a convex combination of one of the vertices and measure on the center circle, right? So here the orange line is, well, basically take a point on the orange line. There is a unique T that gives you the coordinate of this point with respect to center and this vertex, right? And then, for example, for this one, you would consider, let's say, these 2 points. Yeah. Okay, so we are, and so this is that deformation attraction that I was talking about. So we are, well, this is essentially the identity on these polygonal measures. And this is the space onto which my Vittori strips complex, metric thickening deformation tracks onto. So to prove that the Vittori strips metric thickening is homotopy equivalent to this wedge of circles, I want to prove that this guy is actually homotopy equivalent to this wedge of circles. Sorry, wedge, join of circles. Yeah. And so how do we do this? Well, first of all, one can really define an explicit equivariant map, which ends up being homotopy equivalence. Yeah, so this is the definition. To kind of, it looks a little scary, but really, this is in terms of this, like the previous observation, this is in terms of sort of figuring out how to write each point using the center circle and one of the, like, the boundaries right? So it doesn't have to be a vertex. Sorry, I am kind of like, it's also could be like a boundary, for example, right? So this is sort of what it's doing. And the way we prove it is really by induction. So the back, well, I mean, it's some work to prove that the back square is a push out, the front square is a push out. This is just basically a property of a join. And then we also, you prove that it's a push out of CW complexes, right? You also prove that this is a cofibration and this is a cofibration. I mean, basically because it's an inclusion of CW complexes. And then by induction, you prove that these guys are homotopy equivalences, and that gives you a homotopy equivalence. So now we also want to prove that it's an equivariant homotopy equivalence. And we do that by looking at fixed points. Yeah, so this lemma says that it is enough to look at the fixed points. And we also observe that it is enough to look at groups Zn, where n divides to k plus 1, because the rest of the subgroups of S1 and S1, including S1, doesn't have fixed points. And the rest of the subgroups also don't have fixed points. So it's just looking at these ones. Again, we define, well, so what happens here? So we define this map, and what this map does, we'll have a picture. I mean, it's kind of tedious to define these things, but really geometric idea is, again, quite simple. So it takes these measures and then it sort of duplicates them around the circle, however many times. So if it's n, then it's going to be, so if n is 3, then it's going to be this 3 times. And so what this map does, it's a nice map. It descends on our spaces that we're trying to, so the spaces to which Vittori-Schip's metric thickening is deformation refracts to. So it descends to these spaces. And it turns out that it's homeomorphic onto its image. And then we define similarly a map on these circles. Sorry, circles on a join the circles on spheres, essentially using the same map. Yeah, and then the fact that it's homotopy equivalence really follows from the smart definition of this map, and just observing that, and also inductive argument, right? So we show that this is a commutative diagram, and then therefore it's homotopy equivalence, and therefore it's also what I was saying, that this map is a homotopy equivalence on fixed points. Okay, so this is the proof. As maybe often with geometric proofs, it just takes a while to get into the right state of mind to figure out like the right way of seeing things. But after that, it's sort of fairly like straightforward, I guess. So now in the remaining time, I want to talk a little bit about what one can do from here. Because there's a lot of questions that one can try to answer with perhaps similar methods. Well, so if you consider, oh, I think I'm missing a picture. Oh, no, well, it's here. Anyway, if one considers a similar thing, but you do metric thickening on check complexes instead of, and also just, yeah, so metric thickening on check complexes. But you take intrinsic metrics, so you don't do balls in R2, you do balls in the circle and complexes. So people don't know the equivariant homotopy type. There are things known about, there are things known about just homotopy type. Right here, I'm giving the definition, but and also a picture. So a picture is so you take a covering, and then whenever you have intersections, those are recorded as edges, and 3 intersections recorded as a simplex. And then they are different from Vittori-Schip's metric thickenings. They happen at different scale parameters. And different fixed point sets, but yeah, but they also like odd-dimensional spheres. Another open question is, well, let's consider Sn with this group action. What happens there with Vittori symmetric thickenings, with check complexes, with check metric thickenings? There is very little known about Vittori symmetric thickenings of spheres, and I guess Vittori groups of spheres in general. So this is what's known. Or rather, I mean, this is what's known, right? So that here we know, here we also know, and then, yeah, it's wide open. And potentially the methods that I was presenting to you could be also used to tackle this problem. And what else am I saying? Well, yes, and again, right. So then, and also a question about Vittori-Rip's check metric thickening of, oh. Let me actually skip. Okay, I think that's pretty much it. Yeah, thank you.
Are there any questions? Okay, I have one, as usual. Can you go back a couple of slides? Yeah, and, no, the other one for the what this one. So this is the Vittori-Rips complex of Sn, and we know only a very limited amount.
Yeah.
For the check complex of Sn, we know something similar, or
yeah, something similar, which is pretty much nothing.
Okay.
I mean, rather,
I mean,
actually,
more.
let's see. So I'm just like really afraid of having made a typo here, and that should be actually check. But yeah, like.
And this, okay, I see. This might be check also.
Yeah.
Okay, well, in any case, I will ask you the reference later.
Yeah.
Okay.
I'll double check.
Thank you. If there are other questions?
So can you go on it was one of the first slides with the theorem with the homotopy equivalence? Yeah, that after, yes. So is there any intuition why you have like this gap? Because you have like a homotopy equivalence for R in some range, then there is a gap between the right hand and pi, and then you have this homotopy equivalence after pi. So is there some intuition of why you skip between the right hand of the interval and pi?
It's not really being skipped. I mean, if you look at this picture, it sort of depicts what's happening. It's just you have, so here this interval would be, that would be the beginning of the next interval, right? And then, the next one would be the next one. So you really have, we have the knowledge for each sort of scale parameter, or like each interval. You get these ratios, right? And it's not skipped. Okay. It's just, you have to picture, this ladder going up and up and up.
Right. No. Okay. I just misread before. Okay.
No,
sorry.
No worries. Yeah.
Another one. Just to clarify, I haven't understood. So when do you get odd spheres? Odd dimensional spheres? Or products of odd dimensional spheres? Do they happen to be there?
In this thing, they're all odd dimensional spheres. Like in the homotopy
products.
Products don't happen here. So it's well, in the proof, you sort of glue something that is I don't know, maybe here, right? And we have some kind of products, right? And then you glue them along the boundaries and you end up having a sphere. So it's I don't know if that
was it a similar situation for the Vittori-Strips complex of S1, or was it different?
To be honest, I don't know that proof. So like, I'm not that familiar with proof for Vittori-Strips complex. So I can't really say how it exactly that one goes. But the homotopy type there is, I mean, I'm not sure. Yeah, homotopy type there should be the same.
Well, if there are no more questions, we can thank Eugenia again. Then let's resume. Now we have Nicola Sadovec, which we talk about complex analogues of Tufberg-Riccica conjecture and central transversal theorems.
Thank you very much. And thank you to the organizers for inviting me. So this is joint work with Pablo Soberon, and it's concerning, can you hear me all right? Okay. And it's concerning, so these two results, Tverberg-Riccica conjecture and central transversal theorem, they're basically results in discrete geometry, discrete and computational geometry. What we did was we were trying to find complex analogs of these results. And okay, I'll explain what they are and what this means for me. So okay, let me, and stop me if I'm writing in small letters, please. So the first result that one of the results that initiated topological combinatorics, which is where this work lies in, is the famous ham sandwich theorem. It says if we have D nice measures, nice probability measures, I will drop probability so they all have the total measure is 1. So if we have nice measures in RD, then there exists a hyperplane, and by this I mean affine hyperplane, so codimension one thing and also possibly translated. That halves each of the measures. So in symbols, this is saying something like this. So H is a hyperplane, and then I have two sides, plus and a minus, with some orientation. And this is saying we have half of the measure on both sides. Nice measure, I think it'll be fine to just consider measures that are absolutely continuous with respect to Lebesgue measures. So they're integrals of functions. And this was proven by Steinhaus in 1938. This is an old result. Then on the other hand, maybe I'll use this part of the board. We have Rado's central point theorem. So we're kind of getting close to this part. Actually, I'm going to call it center point, which is saying if we have one measure, again, nice measure in RD, then there exists a point such that whenever we take a hyperplane through this point and we look at its positive side, let's say this is even the half space. So we take any half space through this point, and we see how much of the measure is in this half space. We always get this portion of the measure. Let me draw some pictures. And then there'll be a third theorem, which is this one, which is going to be in the middle. So this one says we're in R2. So we have two measures, one blob, another blob. There exists a hyperplane. So this is a line that halves each of them. And this is H. And H plus, H minus. Over here, we're in R2. We have one measure, and we have a point such that whenever we put a hyperplane through it, and however we rotate it, we always get 1/3 of the measure. And you might think, is 1/3 really the best we can do in this case? This seems like a kind of a half, if maybe. But a measure can be kind of supported with 1/3 or 1 over this number at like affinely independent points. So here this rod-on point is going to be something like this. And then whenever I have a hyperplane, I'm supposed to get at least 1/3 on each side. So 1/3 is really the best you can do here. Okay. And why am I writing it like this? There, we're requiring an existence of something of dimension d-1, a hyperplane. Here, point is a dimension 0 affine subspace. Can we have like a result that interpolates? Okay, this was proven by Rado in maybe 1946. Can we have a result that interpolates between them in the sense that we have some number of measures, and the object that we require to exist is k-dimensional for any k between 0 and d-1. And this is the central, so maybe I'll put a line like that, central transversal theorem. So we see that the number of measures, this is over there, it's d, over here it's 1. So let's say, and we're interested in finding affine k subspace that sort of transverses nicely through all the measures. So in this case, we'll be having k plus 1 measures in RD. And we require existence of a k flat. K flat is a name for a k-dimensional linear subspace, possibly translated. B. Such that, and the condition is kind of similar to this. So whenever I have a half space that contains my V, I'm gonna, and I look at each of the measure mu I, I look at a half space, I get at least, and then the fraction ends up being this one, and this is for every I. Here. Let me draw a picture. So if we're in R2, we have a 0-dimensional thing and 1-dimensional thing. There's nothing in between. But if we go to R3, then we have 0-dimensional thing, 2-dimensional thing, and then maybe this would be a line. So in R3, and we have two 3D measures. What this theorem says is there's going to exist a line. So this pierces out. And this is V, such that whenever we have a hyperplane through it, so something like this, and we look at the intersection, so something like this, and however we rotate this hyperplane, we're always going to get, in this case, I don't know, 3 minus 1 plus 1, so that's 1/3. Okay, thanks. So this is central transversal theorem, and this was proved by Živaljević and Vrečica in 1990, and independently by Dolnikov in 92. And this, I mean, you can kind of feel it. Okay, here we're looking at all the K flats. So this is some Grassmannian. So this is, the proof is topological. We're parametrizing all the K flats. So that result over there is really, and this one implies both, because if we require this to be d-1 dimensional, and we look at the all half spaces that contain it, these are just the two. So that's that case. Case 0, that's just this. Okay, this is a nice result in between. Ham sandwich is a classical mass partition result, which says we have some number of masses and we want to partition them equally or in some other way with some kind of partitions of RD. In this case, the partition of RD is just on two half spaces, but you can require different stuff. So if I have time at the end, I'd like to maybe advertise some other open mass partition results that we might want to look at, but that's sort of that story. And then over here, we have kind of an existence of something that transverses through the mass nicely, meaning it's kind of a central point of a mass. So there's this whole area of set transversals where you have a bunch of convex sets in RD, and you're looking for some nice subspace that transverses through all of them, basically just touching them and nothing more. And in this community, people have started to express interest in finding these K-flats that are also complex subspaces. So not just real affine subspaces. So in that case, we would be living in R2D, which is also CD. And then we require additional structure on this thing that it's a complex subspace. And then the question is, can you get such results? And people there started to care about those results. So what we did with Pablo was, one of our results is getting a complex analog of this, where we require the subspace to be complex. So in the interest of time, when did I start? I didn't. Okay. I have time. Okay, so I will write the full results. So this would be kind of the first half or the second half of the title. And then I'll explain how it's connected to the first half of the title. So we managed to get something like this. This is the complex analog. Okay, should write bigger. And the result is for any K+1 masses in RD in CD, the same number of masses, there exists a complex K flat such that whenever we look at a half space containing it, and this is a real half space in CD, which is R2D, we get this portion of the mass. And then, okay, we have the same number of masses, but we get, because we require additional structure on V, we can only guarantee smaller amounts, so to say, of the mass that is contained in this half space. And you can think how they're related. It seems that they're totally unrelated, since this is optimal in both the number of masses and this fraction. Like, you can't. Oh, sorry. It's okay. Did I write it somewhere? So this is I don't think I did. So this is a half space. So H is a hyperplane and H plus is one of the half spaces. Okay, I think I wrote it only there, but H plus, it was everywhere, just a half space, a real half space. Sorry, thanks. Real, yes. Because in order to measure it, we need to partition the space. Okay, and this was part of our motivation. And then how does this all connect to Tverberg-Bretica conjecture? Well, that conjecture is a discretization of central transversal theorem, which actually implies it. So it's kind of also a generalization and discretization at the same time. It is also a generalization of Tverberg's theorem, which some of you might know. So maybe I'll start from there and see how we circle back to these transversal results. Okay, so Tverberg's theorem. This paper is in the archive since like a month ago. So if you want, you can check it out. Tverberg said in 1966, I think, that whenever we have d plus 1, r minus 1 plus 1 points in RD, we can partition them. So there exists a partition of this set of points. There exists a partition into, these are some parameters. This is R, well, that many parts. So I can split into R parts such that the parts have intersecting convex hulls. Like this. Let me draw a picture. So if we're in R2, okay, this is a small picture. I presume. Okay, this is my R2, and I have 4 points. I can always split them into 2 parts such that convex hulls intersect. So if this is one part and this is the convex hull, this is the other, they intersect. If I am in R2, so this is d equals 2. I'm in R2, and I'm looking at partitions into 2 parts. If I'm looking at the partitions into 3 parts, then I don't know. I take a look and I see that if these are my 3 parts, so a triangle and 2 pairs, the 3 convex hulls intersect at this point. Okay. This was proven with methods from discrete geometry, originally by Tverberg. There have been many other proofs, like using colorful Kara-Teodori and stuff like that. But people also went and generalized this problem. So what they did was they said, okay, so here I have 7 points, but I can think of this as a map from the 7 simplex sitting somewhere and mapping it affinely here by mapping vertices to vertices. And then the question is, does there exist a triangle? So this is a face, an edge, this is a face, and an edge, this is a face, such that when I map them, they map to they contain a point. So the so-called topological Tverberg theorem was introduced, which is kind of generalizing this concept. It says, so we can think of this as a map. So for any map from the simplex, which is supposed to have this many vertices, so the dimension is 1 less. So I'm just going to write the dimension in the index. I hope you can see this. So this is my map here, which was affine in this case. And the map is just required to be continuous instead of affine. So in other words, these faces don't have to be really convex hulls. They can be really just images of the face up there by a continuous map. So if we require this map to be continuous, that's the topological part of this problem. Then there's gonna exist R faces of my simplex. I'm gonna drop the index, which are pairwise disjoint. This is precisely corresponding to the partition because this A1 can be seen as a face up here, and since they're disjoint, I mean, it's a partition, that means that the faces were disjoint. So that's what I require. And I require that their images, so this is going to be the convex hulls, if the map is affine, intersect. They'll have a common point. And then this was proven if this number R, the number of parts, the number of faces that we're looking at, is a prime number at first. And this was proven by Barany, Schlossmann, and Sich. And then it was generalized to prime powers by Ozaidin. And if you look at Matuszek's book using the Borsuk-Ulam theorem, which you need the generalization of this theorem to prove this result, which was written at this point, I think he has a sentence where he says, well, we know it for primes. It has been verified for prime powers, but it probably holds outside of that case. We just don't have the methods at the moment. So this was maybe 1988. And then it was proven not to be true when R is not a prime power by Blagojevich, Frick, and Ziegler in 2015, which really, I think, opened a lot of questions because proofs were topological, so it seemed that topology was really driving even the correctness of these statements. Okay. So this is Tverberg's theorem, and let me just say how these two boards are connected. Tverberg's theorem, we can look at that one or we can look at this one, generalizes Rado's center point theorem because maybe I can use another color just for a second. So this, I just want to say that Tverberg implies Rado. So Rado says, I'm giving a mass and I want to find a point in the middle. What I do, I discretize the mass. I approximate it by delta Dirac measures with enough points. And if I choose the number of points to be the number for certain R big enough, from Tverberg's theorem, I don't know, let me just draw a picture like this. So now so I want to prove Rado's theorem. I approximate the measure. Now I have that number of points. I can apply Tverberg's theorem, meaning there is a partition and there is this point that belongs to all the convex hulls. And this point is going to be this P. Why so? Well, because if I have a hyperplane going through it, the half space, since it goes through P, and P belongs to a convex hull of AI, it's going to contain at least one point from each AI. It's going to contain at least R points. And R related to the number of points is approximately 1 over D plus 1. So I'm containing at least this fraction of all the points. I approximate, so yeah. And then the question is, and I'm not sure, but maybe this is how Tverberg-Vretica conjecture was phrased by both. The idea was to both extend Tverberg's theorem and maybe also central transversal. I don't know if this was the motivation. So let me go ahead and state it and see how it's related to this. Are there any questions while I erase the board? Mm-hmm. I think it'll be more productive to talk about that after, but that's a great question. Yeah. And there are a couple of open problems in this, in the Tverberg world. Definitely, they're completely, like, it's not understood what's going on, I guess. Okay. So let me just write for short, Tverberg-Vretica conjecture or problem. Okay, picture. So Tverberg's theorem was concerning one simplex, and or one set of points that we want to partition. Now, suppose that we have, okay, let me draw it like this. So this is 4 points in R3. So this is a tetrahedron generically. And then I have another one like this, maybe. And then what I can do is I can look at a hyperplane, linear hyperplane that goes through the origin, and I can project this down. So now in this hyperplane, I know that I have a radon partition for this one. This is the setting of Tverberg's theorem. Once I project, the numbers are fitting. I have this one also. When I project down, this goes in the middle of the triangle. So my radon or Tverberg partition is going to be this triangle and this thing, this vertex. So this is one partition such that convex hull intersect. This is another partition such that convex hull intersect. And the question is, the problem says, can we get this point, which is the one being in all convex hulls, and this point to be the same when I look at all the planes around? Yes? I'll write it down. Yeah. Because if we do it just right, and we find this hyperplane, in this case, two-plane, and we project, and they're the same point, we can take the orthogonal complement, and the orthogonal complement, when it pierces through here, it pierces through here. These two are going to get mapped to that point where orthogonal projection, this face and this triangle face are going to get mapped, so I get them to meet. So it's about parametrizing these two, these planes and finding actually a line that goes through disjoint faces on this tetrahedron and on this tetrahedron simultaneously. So that's the Tverberg-Vretica problem. Can you do that? So let me just write it down. Okay. Okay. So I'm going to write it, and then I'm just going to draw over for the complex analog, just slight modification, and then I think I'll be done. So we call this set S1. We call this set S2. So if I have Si, and I is going to run from something to something. So this is going to be a set of, so R can also vary for different simplices. This many points in RD. Problem says, can you find a K-flat? So this is going to be this line, which is a 1-flat. Can you find the K-flat? And can you find are disjoint faces on each of the simplices. Oh, sorry, in SI, maybe. That's my notation. So these are disjoint. So there's going to be this triangle, and there's going to be one pair of sigmas. There's going to be another pair of sigmas. So these should be disjoint. In other words, it's a partition such that V transverses or touches. So all of the convex halls. This line goes through the convex hall of these 3 points, of this point, of these 2 points, and of these 2 points, right? And the real case, this case, basically was proven when all Ri's are powers of the same prime number, so they're all p to something, and this something can be different for different i's. And there's a condition that there's a parity condition on this d and on this k, the dimension of the flat that we require. And then what we proved was the complex version. So complex. So this is in the same paper. So we wanted a complex K flat in CD. Complex K flat. The number of points is the same. Nope. Let me look it up real quick. Yep. So the number of points, I made a typo here, but I guess who's interested, we can talk later. So the number of points is about twice as big. So it's 2 times d minus k plus 1. And we want this complex K flat to transverse all of them. And I don't have time to talk about the proof, but there's a Grassmannian going on, and it's basically about proving the certain equivariant bundle coming from the canonical bundle over Grassmannian doesn't have a zero section. So it's about proving the certain equivariant Euler class is non-zero. So that's what's involved here. If you're interested, I'd be happy to talk more, but I'll stop here. And sorry for going over time. Thanks.
And one of a quick question. One, only one.
Sorry.
I don't know. You can
Yeah, so this is true really like for every R, no constraints on these R's like in the...
That's the most important thing, sorry. Thank you. So this is, again, if all R's are powers of the same prime. Yeah, great. Yeah.
And do you know that it fails if they are not, or?
I don't know, but that's definitely the next thing.
And okay,
great.
I was only allowed one question, but I'm going to ask 2. So that Euler class, what cohomology does it live in? Some Bredon cohomology, or what kind of cohomology does it live in?
Borel, actually.
Borel,
Borel,
okay.
yeah. And the group is, well, it should be the symmetric group with this many, the product of symmetric groups here. But you can really, since this is a prime power, there's a ZP to alpha I living inside it. So for when P is a prime and R is of this form, you're really looking at the ZP to alpha I in this case, and the product of those. So that's the group, and it's the Borel equivariant cohomology of Grassmannian times. And then you need to model this problem. So this is some simplicial complex that models these disjoint faces and so on. So it's a nice space.
Okay, thanks.
Yeah. But it gets more complicated because there's also a colorful version where you basically add colors to vertices, and then you just impose, can I also get them to these faces to get different colors? Then the complex becomes more harder to compute, and that's wide open. So I don't have time to mention that, but that's basically the big open question here. The colorful version, can we say more?
We resume for the last speaker of the day, which is Balint Shigli, which we talk about McPherson's conjecture on combinatorial Grassmannians. A new beginning. Yes.
Thank you. Thank you for the invitation, and thanks to the Berlin Mathematical School for supporting part of my trip. So today I'd like to talk about combinatorial vector bundles. They are classifying space the combinatorial Grassmannian, also called the Macphersonian, how it is related to the real Grassmannian, the classifying space of real vector bundles, how this relationship could be exploited, and how we try to attack this relationship in our joint work with Pavel Balogevich, on which this talk is based. So instead of my original plan of diving directly and deeply into the technical details of our construction, I think you'll take away much more from this talk if I start out far away and slowly zoom in to the world of the Macphersonian and only give a high-level overview of our approach towards the end. So I'd like to begin with the following claim. We care about computing characteristic classes. This should sound plausible to you. Vector bundles are interesting, and characteristic classes are their perhaps most important algebraic invariants. Just to quickly recall, imagine you have some space B, and consider some cohomology ring of B with coefficients in some ring R. Then a characteristic class is a particular way to associate to each vector bundle over B, like P1 and P2, some element in the cohomology ring of B. This has to satisfy certain naturality properties, but we do not need to concern ourselves with that right now. What's important is that it takes as input some vector bundle and spits out some algebraic object, an element in a ring. Perhaps the most popular examples of characteristic classes of real vector bundles are their Stiefel-Whitney classes, their Euler class in the oriented case, and their Pontryagin classes. These are fairly useful as they contain fairly explicit geometric information. So we do care about computing characteristic classes, but we are talking about combinatorial algebraic topology right now. So for the rest of the talk, I'll focus on computing characteristic classes through combinatorializing vector bundles. To elaborate, consider the following very general setup. Assume you are given some vector bundle, like on the left, and devise a way to associate some discrete object to it, called its discretization. Then instead of asking if you can directly compute the characteristic classes of your vector bundle, you can ask instead if you can calculate these using only the discretization of the vector bundle. This is of course non-trivial because such a discretization typically contains less information, but if something like this worked out, that would be fairly good, because if all things turn out right, the second step in this process, denoted by this dashed arrow, could be completely algorithmic. It takes in something combinatorial, spits out algebra. So there have been some more classical results of this general shape. First, restrict your attention to the special case where your vector bundle arises as the tangent bundle of a smooth manifold. Just for safety, assume that your manifold is compact, oriented, without boundary, all that. Then perhaps the most naive way to discretize such a tangent bundle is to forget about the vector bundle structure altogether and simply pick a smooth triangulation of the underlying manifold. It was then a conjecture of Stiefel and the result of Halperin and Toledo that the Stiefel-Whitney classes of the tangent bundle are completely determined by a triangulation of your smooth manifold. Even better, they provide an explicit formula to compute these classes. At this point, you might ask, is this very naive setup good for more? Can we extract more characteristic class information? What about, let's say, Pontryagin classes? Well, thanks to the work of Milnor, we know that this is not possible. There are distinct non-diffeomorphic smooth manifolds which have isomorphic triangulations, yet have distinct integral Pontryagin classes. There is, however, the slightly weaker construction of a rational Pontryagin class, which, still sticking to the compact-oriented case, thanks to Tom, is known to be completely determined by a triangulation of the smooth manifold. Even better, really, the topological manifold structure of your smooth manifold is enough. You don't need the entire PL manifold structure provided by the triangulation. So at this point, Gelfand and Macpherson enter the scene and suggest the following. Throwing away the entirety of the tangent bundle is quite wasteful. So instead, alongside your original triangulation, take note of some additional combinatorial objects called oriented matroids, which are somehow ought to measure how this triangulation interacts with the tangent bundle and tries to save some more information from the bundle. Then there is hope that with this extra data, this particular way of discretizing vector bundles or tangent bundles would be good for more and would contain more characteristic class information, maybe even be enough to reconstruct the tangent bundle. They show that this works fairly well, that the rational Ponti eigenclasses of the tangent bundle are completely determined by the discretization process, which is of course not surprising because those are determined purely by the triangulation alone. However, using their additional oriented matroids, they provide an explicit formula to compute these characteristic classes. Now this formula takes in an additional input, a so-called fixing cycle, whose existence is not known for general vector bundles, but in the special case of tangent bundles, which is illustrated here, they claim a formula for calculating one of these cycles and therefore making their machinery towards computing the Ponti eigenclasses work. Not much later, McPherson abstracted away many of the methods which went into this construction into a bundle theory of so-called combinatorial vector bundles, which itself is perhaps better presented in the later paper of Anderson and Davis, where they also spell out how this approach of Gelfand and McPherson can be used to discretize any vector bundle over a non-pathological base space, not just tangent bundles. Then in the same paper, Anderson and Davis show that the Stiefel-Whitney classes of any vector bundle are completely determined by the combinatorialization of said vector bundle. And so this result is slightly more general than that of Halpern and Toledo because it's applicable for all vector bundles. However, it's also weaker because a priori there is no explicit formula to carry out the computation. And so with the hope that this new 30-year-old discretization method, we can compute more characteristic classes. In the rest of the talk, I will focus on the setup of Gelfand and McPherson and try to explain it more in detail. So to understand their discretization process takes two steps. First, we want to view vector bundles as bundles of vector configurations. So traditionally and informally, a vector bundle is just the assignment of a vector space to each point in the base space, such that this vector space varies continuously as you vary the base point. What we want instead is to assign vector configurations in Rk to each point in the base space, which in some even more informal sense vary continuously. Thankfully, this conversion between vector bundles and these equivalence classes of bundles of equivalence classes of vector configurations can be done. And so in the next step of the discretization process, we can forget precisely which vector configuration we assigned to each base point and remember a combinatorial shadow of these vector configurations instead, called their associated oriented matroids, thereby obtaining a function from the base space to a set of oriented matroids, which will be called the discretization of the vector bundle. So the first step of this process is essentially just a non-textbook perspective on constructing classifying maps of vector bundles. To elaborate, the theory of vector bundles, just like the theory of G-principal fibril bundles or spherical quasi-fibrations, is a well-behaved bundle theory in the sense that it has a classifying space, which is characterized by the following property. Fixing any base space B, non-pathological, there should be a bijection between the set of isomorphism classes of bundles over B and the set of homotopy classes of maps from B to the classifying space. Therefore, if you have such a well-behaved bundle theory, understanding it is more or less equivalent to understanding the topology of the classifying space. In the special case of rank K real vector bundles, this classifying space is none other than the Grassmannian of K-dimensional subspaces of R infinity. Now, next, I'll try to explain a way to construct to a rank K vector bundle its assigned classifying map. Imagine this left-hand side as some vector bundle. Then what you should do is first take some global sections of your vector bundle such that they satisfy two properties. One, they should together span every single fiber of the vector bundle, and two, locally speaking, only finitely many of them should be non-constantly zero. So if this is now reinterpreted as a local trivialization of your favorite rank 2 vector bundle, then you can see that these three sections are good because, well, there are only three non-vanishing sections in the picture, which is finitely many. And for example, this highlighted fiber is spanned by the three vectors inside it specified by the three sections. This fiber is spanned just like that, and this fiber is spanned too. So now you get a function from the base space to the set of vector configurations in Rk. Well, this is not entirely rigorous, of course, because if you change the local trivialization on the left, then probably I should highlight it. Of course, because you have these sections above your base space. In each fiber, you have a vector configuration, and you assign that vector configuration to the point of the base space, right? So this is not entirely rigorous, because if you change the local trivialization, then the identification of these fibers with RK might change as well up to a linear isomorphism. And so what you really get is a function from the base space to the set of vector configurations modulo the action of the general linear group on RK. This set, if you sit down and think about it for a bit, turns out to be essentially just the Grassmannian of K-planes in R infinity. So there is a canonical bijection between these two sets, along which we can identify them. Yes, moreover, this function, again, which just takes sections, takes the induced vector configurations above each point and selects their equivalence classes, turns out to be continuous, and just the classifying map of your original vector bundle on the left. Now, the next step, as promised, is to forget precisely which vector configurations we assigned to each base point, and rather only remember some associated combinatorial shadow, the associated oriented matroid. This will be done through a function called mu, which takes as input some vector configuration, more precisely its equivalence class, and spits out some combinatorial data, the associated oriented matroid. In this setting, vector configuration can be formally thought of as a function rho from a set of labels, let's say 1 to n, into Rk, labeling the vectors which participate in the vector configuration. For technical reasons, it's also better to assume that the image of rho spans the entirety of Rk. So we are in the rank k case. Now, calling a subset of labels a basis, if and only if its image labels a basis in Rk, it is not difficult to define the associated oriented matroid of such a vector configuration. Namely, take the family of those subsets of labels which are bases and partition this into two, such that one partitioning set contains all bases oriented one way and the other partitioning set contains all bases oriented the other way. So in this example in the middle, you can see that the labels 1, 2, and 3 label a basis. So the set 1, 2, 3 is a basis of the associated oriented matroid and appears in the construction, while 1, 2, 5 label linearly dependent vectors. So that's not a basis of the associated oriented matroid and doesn't appear anywhere. Moreover, 1, 2, 3 and 1, 2, 4 both appear as clockwise from our perspective. So they fall in the same partitioning set of the associated oriented matroid, while 1, 3, 5 is oriented counterclockwise and falls in the other partitioning set. Now, in general, oriented matroids are not always associated to vector configuration, but rather defined by some abstract axiom systems, just like ordinary matroids. And in particular, this function mu is not necessarily surjective. Now, you might also want me to say that, of course, if you change a vector configuration up to a general linear transformation, that doesn't change which labels label bases and the relative orientations of these bases. So the associated oriented matroid remains the same, and mu is indeed a function from this quotient set. To simplify notation, write mecpkn for the set of these rank k oriented matroids with set of labels 1 to n, where rank k kind of refers to the fact that it is associated to a rank k vector configuration, and call this set the Macphersonian. Now we have this function mu from the Grassmannian to the Macphersonian, which I refer to in the abstract as Macpherson's discretization map, probably. So this is not a well-behaved function, because on one hand, its codomain is just a set a priori, so it is discontinuous. But if you just look at the partition induced by mu on the Grassmannian, so you look at preimages of single points, they turn out to be topologically arbitrarily complicated. So it's not an extremely nice partition. However, point set topologically, it is kind of tame. So this partition, in Anderson and Davis's words, it can be refined with a triangulation. In particular, certain combinatorially defined subsets of this Macphersonian have closed preimages. Now, combining these two methods, we get the discretization method. So just as before, take your vector bundle, take your sections with the same conditions, then you have vector configurations above every single point, take their equivalence class, and then forget about the equivalence class and only remember its associated oriented matroid. So this composite function from the base space to the Macphersonian is the discretization of the vector bundle. Now, in the special case, when your vector bundle is a tautological vector bundle over the Grassmannian, remember that the first step in this composition just constructed the classifying map of your vector bundle. So in this special case, it's the identity, and the discretization of the tautological vector bundle is this function mu again. Here, I'd like to point out that this presentation of combinatorial vector bundles and this combinatorialization process, which I gave so far and which I'll continue giving, is not precisely the one of Macpherson or of Anderson and Davis, but it can be made precise. So, for example, in the language of Anderson and Davis, you additionally want to take some triangulation in the base space so that this entire function can be defined using some discrete finite data using the triangulation, but you can drop that condition. And especially in the infinite case, that's better for you. So now we have a method which turns vector bundles into combinatorial vector bundles, where the latter in this presentation are just well-behaved functions from non-pathological base spaces to the Macphersonian. The combinatorial vector bundles turn out to have pullbacks. Simply precompose the structure function eta by the continuous map between the base spaces along which you want to pull it back. As they have pullbacks, you can interpret the theory of combinatorial vector bundles as a sort of bundle theory. And it, just like the theory of vector bundles, turns out to be well-behaved in the sense that it has a classifying space with this property, which is denoted like this, and is also called the Macphersonian. I'll refer to it as the Macpherson as a topological space. Now, again, the tautological vector bundle of the Grassmannian discretized was just this function mu. Therefore, mu is a combinatorial vector bundle, and by the defining property of classifying spaces, must have a classifying map from the Grassmannian to the Macphersonian. This classifying map is denoted by tilde mu. And as the Grassmannian was, again, the classifying space of rank K vector bundles, while the Macphersonian was a classifying space of rank K combinatorial vector bundles, it kind of defines this entire discretization process. So somewhat more precisely, it turns out that discretizations and pullbacks commute. This is somehow a consequence of the fact that when you pull back a vector bundle, you can pull back its sections as well. And so by abstractum sense, Ione dilemma, you get that understanding the discretization process is the same as understanding this continuous map tilde mu. From the viewpoint of algebraic invariance, this also means that our original question of what characteristic class information can be recovered from the combinatorialization of a vector bundle is essentially the same as knowing what kind of morphisms tilde mu induces in different cohomology theories. So the result of Anderson and Davis, which said that Stiefel-Whitney classes of a vector bundle are determined by its discretization, are the same, but is the same in this perspective as saying that tilde mu induces a surjection in mod 2 cohomology between the Macphersonian and the Grassmannian. So in the next few minutes, I'll try to explain what is the Macphersonian as a topological space. It is not the Macphersonian as a set of rank K-oriented matroids with a topology, but rather, as you may be able to guess from these norm signs from Tuesday, and its order complex. In particular, the Macphersonian as a set of rank K-oriented matroids is a partially ordered set, where one oriented matroid is larger than another one if it can be deformed into the latter. To illustrate this, imagine you have some vector configuration like on the left, and take a continuous deformation of this vector configuration such that the associated oriented matroid M remains constant throughout the deformation, except possibly at the very end, where the associated oriented matroid M prime can be something different. So previously 4 and 5 were independent, and here they become parallel to each other. Then in some sense, M prime is in a more special position, right? We had certain tuples in M which were linearly independent, and they degenerate into linearly dependent stuff in M prime. In such a case, say that M prime is a weak map image of M, or in other words, there is a weak map from M to M prime. Now, just as oriented matroids are more general than vector configurations in RK, weak maps are a more general and abstract concept as well. And what I just described was really this lemma, which lets you construct interesting examples of weak maps fairly easily. What's important, though, is that weak maps are not really maps, but rather just a relation between oriented matroids, one which turns out to be anti-symmetric and transitive, and so it turns the set of rank K oriented matroids, the Macphersonian, into a partially ordered set. And then, if you remember from Tuesday, if you have a partially ordered set, you can take its order complex, which, just to quickly recall, is obtained as follows. So if you have a partially ordered set, you can interpret rank T chains in it as abstract simplices with T vertices. And whenever you have a simplicial complex, you can take its geometric realization by taking analogous geometric simplices and gluing them together in the same way. And when you perform these two operations for a partially ordered set, you get its order complex. Now, the perhaps most important open question regarding the Macphersonian is whether or not this continuous map tilde mu is a homotopy equivalence between the Grassmannian and the Macphersonian. It is also stated as a conjecture asserting that it is a homotopy equivalence. If this was true, then that would be pretty great, because that would mean that the classifying space of rank k vector bundles and the classifying space of rank k combinatorial vector bundles, when setting n to infinity, are homotopy equivalent, and therefore these two bundle theories are essentially the same. And so you could study vector bundles through their combinatorialization and vice versa. From the viewpoint of algebraic invariance, this would also mean that the combinatorialization of a vector bundle would contain all characteristic class information of the original. Be aware that if you Google this topic, then the first paper which comes up claims to settle this conjecture in full generality. However, it had to be retracted due to a fatal flaw, so it is still wildly open. Now, let me quickly list some of the more interesting results known in this topic, which are actually true. So perhaps the most elementary observation is that the Macphersonian is always path connected. If you are familiar with oriented or just ordinary matroids, really, this is somehow related to the basis exchange axiom. This can also be rephrased by saying that tilde mu is an isomorphism in the zeroth homotopy groups. There is also the topological representation theorem of Folkman and Lawrence, which is possibly the most important theorem connecting oriented matroids to topology, but which I don't have time to explain today. But one of its consequences is that the conjecture holds for k equals 1. So whenever the rank is 1, tilde mu is a homotopy equivalence, and you can pass between. This is a homeomorphism, actually, I think. Bis was claiming only a homotopy equivalence, I think. Yes. Yes, so k equals 1, conjecture is 2. You can pass between rank 1 vector bundles and combinatorial vector bundles. In his PhD thesis, Babson also proved something similar for k equals 2. So for rank 2, we also have a homotopy equivalence of these two classifying spaces. However, I find this thesis fairly difficult to read, although excellent for formalization. So I haven't checked the details because it is fairly difficult to read, but we'll get back to that. So rather, I suggest reading this paper of Anderson, where she gives a better explanation for the same claim, as well as establishing many facts about the homotopy groups of the Macphersonian, mostly stabilization results, and also that tilde mu induces an isomorphism in the fundamental group as well. Therefore, the fundamental group is not a strong enough algebraic invariant to distinguish these two spaces. In a later paper, Anderson and Davis built on this previous result, as well as the topological representation theorem, to prove a whole bunch of stuff, namely what I previously mentioned, that tilde mu induces a surjection in mod 2 cohomology, one proof of which also directly generalizes to mod 3 coefficients, but fails to generalize any further. Some concrete computational results on the morphisms on homotopy groups induced by tilde mu, as well as the fact that tilde mu is an isomorphism of the second homotopy groups as well. So now the observation of Mav and Ziegler is fairly elementary, so let me quickly remove it from the slide and rather start talking about our approach with Blagojevich regarding this problem. So our goal was to apply homotopy theoretic tools to attack the question on the top of the slide. And starting by modifying some methods of Richter and Sturmfels regarding realization spaces of oriented matroids, we managed to unify multiple of these results. So we got a unified proof for the conjecture for k equals 1 and k equals 2, as well as a homotopy theoretic approach to proving that tilde mu induces an isomorphism of the fundamental groups, replacing the original very combinatorial and down into the details proof of Anderson using bistellar flips. which, however, can be reused when combining with even more homotopy theory, for example, Farajun's homotopy colimit formula, and our methods to give a new proof of the second homotopy group result as well. So unifying these is all nice and such, but you'll be probably more delighted to learn that using all tools, we managed to prove the case 3, 6 as well. So if k equals 3, n equals 6, then tilde mu is also a homotopy equivalence. Pretty good on time. So a few words about our methods. It all starts by first writing the Grassmannian as a colimit of some of its subspaces, where we construct one such subspace, which we call a specialization space, for each oriented matroid in the associated Macphersonian. These are defined using this Macpherson's discretization map and also the concept of weak maps, this partial order, but their definition for now is not really that important. We don't know much about their topology, but they are fairly well behaved in the sense that they are just subcomplexes of a certain triangulation of the Grassmannian. And as they form a diagram, alongside their colimit, there is the other associated topological space to this diagram. It's homotopy colimit. This is also a topological space which comes equipped with a continuous map to the colimit, now which is the Grassmannian. And we check that this diagram is well behaved, and therefore this continuous map is a homotopy equivalence, letting us pass from the Grassmannian to this homotopy colimit construction. This is good because it lets us apply more homotopy theoretic tools to the problem. As we know, homotopy theory works rather badly with colimits, but works well with homotopy colimits. For example, if you know some basics about homotopy colimits, you probably know that if you take the homotopy colimit of a constant diagram of points, that simply recovers, let's say, over a partially ordered set, that recovers the order complex of said partially ordered set. And because homotopy colimits are natural as well, we get a new natural construction of this map tilde mu from the Grassmannian to the Macphersonian, which in the case n equals infinity is just as difficult for finite n, in contrast to Anderson and Davis's involved combinatorial approach, which gets significantly more tedious to work with for the interesting case of n equals infinity. I'd also like to point out that this is natural both in the everyday and the categorical sense of the word. So now, because this is defined as a natural transformation between homotopy colimits, it's a direct application of the homotopy lemma to see the following corollary. If all specialization spaces are contractible within a given Grassmannian, then tilde mu is a homotopy equivalence between these two classifying spaces. And this gives us a new angle of approach for attacking this conjecture, and also illustrates the general shape of our work so far. So we prove certain properties of the specialization spaces, typically with homotopy theoretic tools and induction on oriented matroids, and then apply some more homotopy theory to get corollaries regarding the Macphersonian. So for example, using that previous corollary and this proposition stating that specialization spaces are contractible for all known cases of the conjecture, as well as the new case of 3-6, we get to reprove the previous result of Babson and as a consequence of the topological representation theorem, and extend it to 3-6 as well. With respect to algebraic invariance, we managed to prove that these specialization spaces, unlike realization spaces of oriented matroids, are always non-empty, path connected, simply connected, and as I promised, by reusing the combinatorial methods of Anderson, they are also two connected. From here, it's simply an application of a theorem of Björner, which itself is a modification of Quillen's fiber lemma, to get new proofs for the fundamental group and second homotopy group isomorphism results as well. In case you are skeptical regarding the conjecture, you will be probably delighted to learn that we have two spectral sequences connecting the cohomologies of the Grassmannian and the Macphersonian, which could possibly be used to disprove the conjecture if we understood small specialization spaces, and we found a non-contractible counterexample thereof. So that's essentially all. In the remaining 45 seconds, a quick recap. So I talked about how characteristic classes and our desire to compute them motivates the study of combinatorial vector bundles, and there's some hope they contain this characteristic class information. Then we saw how vector bundles can be converted to these bundles of equivalence classes of vector configurations through interpreting their classifying maps in a particular way. How you can convert vector configurations into oriented matroids using this function mu, how it relates oriented matroids to the Grassmannian, and how it can be combined with the previous point to produce a discretization process for vector bundles. Then how the original question of what characteristic class information can be recovered from the combinatorialization for vector bundle is essentially the same as understanding the cohomology of this map, tilde mu. And then at the end, I listed some of the interesting results, and as well as our approach using specialization spaces and homotopic limits to unify some of these results and extend them to the new case of 3.6. Thank you very much.
Any question?
Could you maybe be a bit more formal now about how you construct the Macphersonian?
The Macphersonian. Let's see, then go back to weak maps of oriented matroids, probably. So oriented matroids, let's see. So I define them as these partitions of bases, and they should satisfy certain axioms. And then a weak map is essentially the same, you just decrease both partitioning sets simultaneously. So if you throw away bases from both partitioning sets such that you still get an oriented matroid, that's a weak map of oriented matroids, right? And that defines this partial order. And once you have the partial order, you can take its order complex, which is the Macpherson as a topological space.
What? Oh. Okay, thanks.
Yes.
I mean, like already this 3.6 is pretty good, I think, but like, what is your hope? How far do you think you guys can get with this new method?
So here, the point where the Richter and Sturmfels methods came in was that we modified them to prove that these specialization spaces are contractible. In the original paper, they prove contractibility of realization spaces of oriented matroids for 3.6, 3.7, and 3.8. And I believe that our modified methods should also work for 3.7 and possibly for 3.8. But unlike them, we haven't yet found a nice way to package these methods. So one of the things I'm working on right now is a computer program to first check 3.7 and 3.8, because now it can be checked completely algorithmically. There are just a few million or billion cases. And then if that works out, we can work on packaging that. The other main project for the close future is that there's this paper of Michael Dobbins, which he published a few years back, where he constructs a different setup towards attacking this conjecture, which, as far as I know, haven't produced any explicit stuff like this, but there is a non-vanishing chance that if we apply our methods to his setup, then that might prove the rank 3 case. And then my personal belief is that rank 4 and onwards is probably not true. So, but we shall see.
Thank you.